How could space have an edge if it's everything? It turns out that it has more than one, and each one has its own rules. Tonight, we'll look for the real limits set by physics. These include the particle horizon, which shows how far light has traveled, the Hubble radius, which shows how far recession has gone, the future event horizon, which hides data, and the shells that can be seen, such as the CMB's last scattering surface. We will also map useful cutoffs, such as the heliopause, the Oort Cloud, and the splashback ends of galaxy groups. There is no philosophy, only measures. We can see some limits, but we can never cross them. You'll also understand why the end of the world is always moving. Observable universe versus entire universe. People often ask where the universe ends, but they really mean two different things: the edge of what we can see and the size of everything in the universe. The observable universe is the sphere from which signs have had time to reach us since the hot Big Bang. It is defined by the time it takes for light to move and the growth of the universe. The farthest galaxies we can see now aren't 13.8 billion light-years away, because space has been stretching while photons have been traveling. Instead, they are about 46 billion light-years away, which makes a viewable sphere about 93 billion light-years across. This edge is not a wall in space. It's a limit in time and cause and effect, set by how long the universe has been around and how growth makes distances bigger. The entire universe, by contrast, is whatever lies beyond that horizon, and it may be vastly larger than our observable patch. It could even be spatially infinite or finite, but unbounded like the 3D analog of a sphere's surface, where you can travel forever without hitting an edge. We don't know yet, because information from beyond our particle horizon simply hasn't had time to arrive. This is why phrases like end of the universe are slippery. There may be no physical cliff where space stops, only places forever beyond our light cone. How far depends on which cosmological ruler you use. Look-back time counts how long a photon has been traveling. For the most distant galaxies we see today, more than 13 billion years. Proper distance asks, how far are those galaxies now? Which is where the tilde 46 billion light-year figure comes from. Angular diameter and luminosity distances tell different observation-friendly stories about size and brightness, as expansion redshifts wavelengths and thins out photon energy. None of these distances are wrong. They're tailored to different questions. The cosmic microwave background, CMB, provides a practical photonic shell for our view. A surface of last scattering formed when the universe cooled enough for electrons and protons to combine into neutral hydrogen, letting photons stream freely. That happened about 380,000 years after the Big Bang, placing a hard ceiling on how far we can see with ordinary light. Earlier times were opaque, but even here, there's no literal curtain hanging in space. We see back in time to a hot, dense plasma that once filled everywhere. The CMB sphere is just the set of points from which those ancient photons are reaching us now. Observers in a faraway galaxy have their own 93 billion light-year sphere that is focused on them. In some places, it overlaps with ours and leaves out others. If you could teleport to a galaxy 20 billion light-years away, in coordinates that move with you, parts of the sky would be forever hidden from us, and we would lose some of the ones we can see. Yes, that is a paradox. That's just how boundaries work in a space-time that is expanding. So does the universe end beyond what we can see, not in any way our current physics demands. What we can say is that our measurements, galaxy surveys, supernovae, Baryon acoustic oscillations, gravitational lensing, and the CMB, paint a cosmos that looks statistically the same on the largest scales we've probed. That uniformity, plus tight constraints on spatial curvature, hints we're not perched near some special border. If there's an outer limit, it lies beyond our causal reach. If space is finite, its wraparound scale exceeds our current horizon. If it's infinite, there is no outer edge to hit at all. Hubble radius, particle horizon, event horizon. There are three main distances often called the edge of the universe, but each one represents a different kind of limit. The first is the Hubble radius, which can be written as r sub h equals c divided by h naught. In this equation, c stands for the speed of light, and h naught represents the Hubble constant. Using today's estimated value of about 67 to 74 kilometers per second per megaparsec, the Hubble radius comes out to roughly 14 to 15 billion light-years. At that distance, galaxies appear to move away from us at the speed of light, not because they're speeding through space, but because space itself is expanding. This doesn't break Einstein's rule that nothing can move faster than light, since it's the space between galaxies that stretches, not the galaxies themselves. The Hubble radius also isn't a hard boundary. We can still see galaxies beyond it because the light we detect left them long ago, when the universe was smaller and its expansion slower. As space grew, those photons continued traveling toward us, eventually arriving even though their source galaxies have since moved much farther away. There really is a cause limit, but it's not the same kind as the particle horizon. It's the farthest that light could have moved in one direction to reach us since the Big Bang. Since that light traveled through a universe that has been growing for 13.8 billion years, the particle horizon radius is now about 46 billion light-years, which covers a sphere that is 93 billion light-years across. Because of this, the observable universe is much bigger than 13.8 billion light-years. The lengths between things have grown, while signs have been sent. Light, neutrinos, or gravity waves from anything past the particle limit have not yet had a chance to affect us, so the particle horizon marks the end of the possible things that could have reached us by now. The question is now about the future because of the event horizon. It asks, what is the farthest distance that light sent out today will ever reach us, no matter how long we wait? Dark energy is speeding up the growth of the universe, and there is a future event horizon that is about 16 billion light-years away, which is the right distance for us today. Right now, things outside that radius can send a flashlight burst toward us, but we won't see it because the distance between us is growing too quickly, leaving the signal stuck. The event horizon is the farthest point in the future that something new can come into view. It helps to visualize a treadmill with dots painted on the belt. The Hubble radius is the point where the belt speed matches your maximum walking speed. You can still see dots that started inside and drifted outward because their earlier steps beat the belt. The particle horizon is how far a dot could have walked toward you since the treadmill started. Dots that began farther away have never had enough time to reach your sight line. The event horizon says that dots currently beyond a certain mark will never make it to you, no matter how long the machine runs, because the belt soon accelerates to a fixed, unbeatable pace. Early on, when matter dominated, expansion was decelerating. The Hubble radius grew, allowing more distant light to cross in. In the dark energy era, the expansion rate tends toward a constant, de Sitter-like. So the Hubble radius approaches a fixed value, and the event horizon stabilizes. The particle horizon, however, keeps growing because time keeps passing. We'll accumulate signals from regions that are currently just inside the event horizon, and from regions between the Hubble radius and particle horizon that emitted their light long ago. That's why the observable universe will continue to reveal slightly more of its past, even as the set of galaxies that can ever affect us with new signals shrinks. Common confusions vanish with these distinctions. If a galaxy is receding faster than light, how can we see it? Answer: because its past light was emitted when it was closer and the expansion slower. Photons rode the changing Hubble radius inward. Is the Hubble radius the same as the observable universe edge? No. The latter tracks the particle horizon. Is the event horizon the same as a black hole's? They're analogous in being one-way boundaries for information, but a cosmological event horizon is set by global expansion, not by local space-time collapse, and there's no singularity lurking beyond it. High redshift is reached by telescopes like JWST that collect light from sources that are now beyond the Hubble radius. Surveys of the cosmic microwave background map the conditions just inside the particle horizon, and studies of cosmic acceleration and large-scale structure find out if there is a permanent event horizon and how big it is. If the quantity of dark energy changed, the future horizon would also change. If acceleration keeps going, most galaxies will eventually become so faint that they can't be seen anymore as their light redshifts and dims rapidly. Cosmic light cones and look-back time. Draw your light cone to find out where the world ends for you. In space-time graphs, time runs up the figure, and space goes from left to right. The past light cone shows the events that could have sent the light that you see now. The future light cone shows the events that you can change by sending a signal. Anything outside of your past light cone is not linked to the past because light, or any force limited by light speed, has not had enough time to make the trip. That line isn't just a work of art. It's an exact, physical definition of what observable means. Because the universe is expanding, cosmologists often use a special kind of diagram called a conformal time plot. In this version of time, called conformal time, light rays always travel along 45-degree lines, even though space itself is stretching. This clever trick turns an otherwise distorted, expanding grid into a clean picture of cause and effect. Light always follows those 45-degree paths, while points in space drift apart according to the scale factor, written as A of t. Your past light cone cuts through layers of cosmic time, each layer marked by a redshift, z, and a corresponding scale factor given by a equals 1 divided by 1 plus z. By tracing that intersection, we can tell when and where the photons we observe today first began their journey. This leads to the idea of look-back time, the amount of time that has passed between when the light was emitted and when we detect it now. It's essentially the most natural cosmic clock for observers. For example, a galaxy with a redshift of about z equals 1 has a look-back time of roughly 7 to 8 billion years, while one at z equals 2 during the so-called cosmic noon, when star formation reached its peak, has a look-back time of about 10 to 11 billion years. The cosmic microwave background comes from a plasma only about 380,000 years after the Big Bang, so its look-back time is almost the full 13.8 billion years. Look-back time doesn't reveal how far away an object is right now, because expansion keeps changing that distance, but it does tell us how far back in time we're actually seeing. To connect clocks to rulers, we pair look-back time with different cosmological distances. Comoving distance freezes the expansion and asks, how far apart would these points be now if we rode along with the Hubble flow? Proper distance asks, how far apart are they at a given cosmic time? Luminosity and angular diameter distances encode how bright or how big an object appears under redshift and dimming. The same photon journey carries different answers depending on your yardstick. The past light cone unifies them by anchoring everything to emission time and reception time. Light cones also explain the trio of edges you met earlier. The particle horizon is the outermost intersection of your past light cone with the universe's earliest times, the farthest place that had time to send any signal by now. The Hubble radius is a kinematic scale embedded in each time slice and can sit inside your past light cone. Photons can originate beyond it and still arrive because the Hubble radius grew in the past. The event horizon appears when you flip the cone forward. In an accelerating universe, your future light cone never reaches beyond a certain co-moving radius, meaning some galaxies you see today are already outside the set you can ever contact. In an expanding universe, photons do not fly on straight Euclidean lines. As they climb out of deeper gravitational potentials and traverse a changing scale factor, their wavelengths stretch, shifting energy to the red. That's why look-back time and redshift are married. The longer the journey through expanding space, the more the photon redshifts. The mapping from Z to look-back time depends on the cosmic mix of matter, radiation, and dark energy, so each precise conversion bakes in a cosmological model. Change those parameters a little, and the same redshift, corresponds to a slightly different look-back time. Putting together the timeline of the world is like doing a tomography practice. The 21 centimeter line of neutral hydrogen promises a 3D movie of the Dark Ages, when the first light sources were still forming. Supernovae and standard candles give luminosity distances at different Z values. Galaxy surveys show how clustering changes with look-back time. Baryon acoustic oscillations are used to calibrate distance redshift relationships. Each tool takes a picture of a different layer of your past light cone. All of them put together make a picture of how the structure has changed over billions of years. What does this have to do with ends? Because you own a light cone. A person looking at the universe from far away has a different cone, which means they can see a different part of reality. There is no one master sky. There are only past light cones that are connected to individual worldlings. In this way, the universe does have edges, but they are not walls in space. Instead, they are limits in space-time that shape what each viewer can ever send or receive. Expansion is not speed through space. Shouldn't Einstein be broken if worlds far away are moving away faster than light? It sounds like it should, until you picture something else. The speed limit in special relativity is the same for things moving through space in any local frame where they are freely falling. But the huge lengths you hear about aren't caused by rockets slamming on the brakes. They're caused by space itself expanding in a measured way. The spacetime metric, which is used to measure distance in general relativity, changes over time. This change can make the distance between two faraway, unmoving galaxies grow faster than light without anyone crossing the path of their neighbor's light beam. Imagine two flags planted on a stretchy field. Neither flag moves on its own. The ground between them stretches. If you zoom in on one flag, the local physics still follows special relativity, meaning nothing nearby, not even light, can go faster than light. But when you zoom out, the rulers between distant flags grow longer because the universe's scale factor, written as A of t, increases over time. The rate of that stretching is described by the equation V sub rec equals h of t times d, where V sub rec is the recession speed, h of t is the Hubble parameter at that time, and d is the proper distance between the 2 points. For large enough separations, this apparent speed can exceed the speed of light, but that doesn't mean anything is actually moving through space faster than light. It's just a way to describe how space itself is expanding. This is why we can still see galaxies whose current recession speeds are faster than light. The light we detect from them was emitted long ago, when they were much closer, and the universe's expansion rate was slower. Over cosmic history, as the universe transitioned from being dominated by radiation to matter and then to dark energy, the Hubble rate h of t changed, and so did the size of the sphere, where recession speed equals light speed. Photons travel through these changing conditions, sometimes moving inward as expansion slows, sometimes getting stuck when acceleration takes over. In a sense, they're surfing across an ever-changing cosmic tide, each wave shaped by the universe's evolving expansion. What about the redshift we measure? Is that just Doppler? For nearby galaxies, small ZZ, a Doppler description works well, but cosmological redshift is best viewed as wavelength stretching with the scale factor, lobs, lemmet, anau, athen lobs, lemmet equals sign anau/athen. The photon didn't lose energy to friction, its oscillations were dilated by the growth of space. In a precise general relativistic treatment, you can decompose redshift into Doppler-like and gravitational pieces along the path. But the neat global statement is that expansion rescales light. Another tough question is why atoms, people, and the Milky Way aren't stretching if space is expanding. Because growth works on separations that are free and not bound. On very small scales, the Hubble flow is slowed down by binding forces like electricity in atoms and molecules, and self-gravity in galaxies and clusters. Einstein's equations have a local solution that looks like a bound system embedded in an expanding background when the potential well is deep enough. The background wins only when it is far from the well. That's why solar systems go around in circles, galaxies spin, groups stay together, and the Hubble dance only includes gaps between galaxies. Peculiar velocity is the second key part of cosmic motion. It's the individual movement a galaxy has on top of the general expansion of the universe, also known as the Hubble flow. These peculiar motions combine with recession speeds like vectors, meaning their directions and magnitudes add together. However, as the universe expands, peculiar velocities gradually fade, shrinking roughly in proportion to 1 divided by the scale factor, a. Over billions of years, this decay causes most galaxies to settle into co-moving motion, where they simply ride along with the expanding space instead of moving through it. This concept helps explain the tethered galaxy problem. If you take a galaxy that's been held at a fixed proper distance and then release it with zero peculiar velocity, what happens? In realistic models of the universe, it eventually falls into line with the Hubble flow. Depending on the universe's expansion history, it might drift slightly toward or away at first, but in the long run, it moves with the cosmic expansion, not against it. Also, headlines like "faster than light" make you think the wrong thing about the message. Superluminal speed is too fast to send a local signal past your neighbor. No runner can burn past a photon in their local lab. The part that is beyond the speed of light is the growing distance between very far away worldlings. You can't just say twice the speed of light, because causal horizons are more important. What you can see is determined by your past light cone, particle horizon, and what you can ever touch is determined by your future light cone, event horizon. Special relativity makes sure that every local experiment is honest within those lines of cause and effect. You can get the wrong idea from the popular space as a rubber sheet comparison if you use it too much. There is no empty space that space can grow into. The metric scale factor goes up, which changes how coordinates and measured lengths relate to each other. So expanding into what? Isn't really a question. The math doesn't need anything else. In addition, expansion is not a force that pushes you. It's just the state that you notice when there are no bigger forces present. Observationally, how we read the sky is based on the difference between moving through space and expanding space. At low redshift, the Hubble-Lemaitre law connects distance and recession in a straight line. At high redshift, supernovae, baryon acoustic waves and weak lensing piece together Hz, and the history of the scale factor. Gravitational waves act as standard sirens for measuring lengths that are not based on cosmic distance scales. This helps us make sure that our story of the expansion is correct. These probes don't just look at galaxies as they explode, they also make maps of how shapes change when gravity acts on them. CMB, the surface of last scattering. The cosmic microwave background, CMB, which is a circular photosphere that surrounds us, is the edge of what light can tell us. This isn't because space stops there, but because things weren't clear in the past. Thomson scattering said that free electrons constantly scattered photons in the early universe, which made the universe look like a bright fog. When the temperature dropped to about 3000 Kelvin, redshift Z1, 100 ZH1, 100, electrons and protons joined together to form neutral hydrogen. This is known as recombination. The fog lifted when there were a lot fewer free electrons. Photons broke away from matter and started moving freely through space. With a blackbody temperature of 2.725 K, those same photons are coming at us from all directions today. They have been stretched by expansion into microwave bands. The round area where most of the last scatterings happened is our CMB surface. Two terms help keep the physics straight. Recombination refers to the atomic transition when ions turn neutral. Photon decoupling is the moment the mean free path of photons suddenly exceeds cosmic scales, letting light travel unimpeded. They're closely timed, but not identical, and together they define why the CMB behaves like a photosphere, a last interaction surface, not a material wall. In the CMB sky, uniformity is extraordinary. Temperature fluctuations are only about 1 part in 100,000. Those tiny anisotropies encode a fossil record of acoustic waves in the primordial plasma. Gravity pulled overdense regions inward, photon pressure pushed back. The tug-of-war drove baryon acoustic oscillations, BAO. When decoupling hit, the motion froze, imprinting a pattern of hot-cold spots whose angular power spectrum forms a series of peaks. The position of the first peak pins down spatial curvature, very close to flat, while the relative heights of peaks reveal the baryon content, dark matter density, and expansion history. In short, the CMB is our cleanest cosmic ledger of initial conditions and large-scale geometry. The CMB also carries polarization. Thomson scattering polarizes light if the incoming radiation has a quadrupole anisotropy. Recombination provided exactly that. The result is a curl-free E-mode pattern detected to exquisite precision and a far fainter curl-like B-mode component. On large angular scales, primordial gravitational waves from inflation could seed B-modes. On smaller scales, gravitational lensing of E-modes by intervening structure converts some power into B. Separating these sources is a major frontier because a primordial B-mode detection would probe physics at energy scales far beyond colliders. Silk damping is another important part. In the past, even before splitting, photons moved from hot places to cold ones, removing small-scale anisotropies. Because of this spread, and the short amount of time it takes to rejoin, the CMB's small-scale power drops sharply above a few arc minutes. That washout isn't a problem with the instruments. It's the mean free path and width of the last scattering epoch, which tells us how fast the universe went from being dark to clear. Not all CMB structures are primordial. The dipole, hot in one direction, cold in the opposite, comes from our motion, approximately 370 km mass, relative to the CMB rest frame, a Doppler effect. At later times, evolving large-scale structure imprints secondary anisotropies. The Sunyaev-Zeldovich SZ effect arises when hot electrons in galaxy clusters inverse Compton scatter CMB photons, distorting the spectrum along those sightlines. The integrated Sachs-Wolf ISW effect occurs when photons traverse time-changing gravitational potentials in an accelerating universe, gaining or losing a bit of energy. Weak lensing by the cosmic web subtly shears and smears CMB features, letting us reconstruct the projected mass distribution between us and the last scattering surface. Why call it a surface at all? Because most last scatterings happen over a relatively narrow slice in redshift and time, producing a visibility function that peaks at decoupling. But it is not infinitely thin. Recombination unfolded over tens of thousands of years, creating a shell with measurable width in comoving distance and angular projection. That width, plus diffusion damping, limits the CMB's ability to resolve primordial structures below a certain scale, nature's built-in blur. The cosmic microwave background, or CMB, has a spectrum that's almost a perfect blackbody curve, strong evidence that the universe began in a hot, dense, and well-mixed state. Any tiny deviations from this perfect shape, known as mu-type and Y-type spectral distortions, would reveal signs of energy being added to the early universe. Such energy injections could come from decaying particles, the dissipation of small-scale fluctuations, or the formation of the first structures. Future space missions are designed to search for these subtle distortions, turning the CMB from just a static snapshot of the early cosmos into a precise energy record of how the young universe evolved. The last scattering surface has thickness. We often show the cosmic microwave background, CMB, as a crisp ring, like a star's photosphere wrapping around us. But nature didn't go from being dark to being clear all at once. In the beginning of time, the universe was a thick cloud of hot electrons and protons that sent light everywhere. As it got cooler, electrons started to settle into atoms. The fog got thinner, and light finally got through. It took a short but real amount of time for that clearing to happen everywhere at the same time. So, the CMB's surface is not a very thin layer, but a layer with a depth that can be measured. Before atoms formed, photons constantly bounced off free electrons, so their paths were tiny zigzags. As the temperature fell, the number of free electrons dropped dramatically. The average distance a photon could travel before the next scatter, the mean free path, grew from microscopic to cosmic. But the electron drop-off was steep, not instantaneous. Over tens of thousands of years, the fog went from thick to thin, and photons went from trapped to free streaming. Most of the CMB photons we see last scattered near the peak of that transition, but a fair fraction escaped a little earlier or later, so the last scattering surface has a finite width in both time and distance. Why does that matter? Because thickness blurs details. Imagine trying to photograph a mountain range through fog that's lifting. If the clearing takes time, your snapshot mixes views from slightly different depths. On the CMB sky, that blur shows up as a gentle soft focus at very small angular scales. Even if the early plasma had sharp features, those features get smoothed as some photons last scatter from slightly nearer layers and others from slightly farther ones. That's one reason power in the CMB's tiny hot and cold speckles drops off at the smallest scales. Diffusion happens before the fog clears, which is a second buffer. Photons moved from hot spots to cooler areas and back again while the material was still invisible. This smoothed out temperature differences below a certain size. Those very small waves were mostly gone by the time the universe became clear enough for light to move easily through it. The limited clearing time and pre-clearing diffusion work together like an anti-alias filter, making it harder for the CMB to see very fine details. This natural blur isn't a nuisance, it's a measuring tool. The shape of the CMB's soft focus tells us how fast the fog lifted and how far photons could wander while the plasma thinned. From that, we infer concrete stuff, the density of ordinary matter, the amount of helium made in the first few minutes, and the general pace of cooling. In other words, the CMB's slightly fuzzy edge is a ruler and a thermometer hiding in plain sight. The same physics explains why we talk about a visibility curve, the chance that a CMB photon lasts scattered at a particular time. That curve rises as the fog thins, peaks when the universe is most transparent, and then trails off. It defines the layer's center and thickness. Because gravity and pressure were driving sound waves through the plasma at that time, different regions were caught at different phases of their compressions and rarefactions when the curtain lifted. The CMB snapshot therefore preserves a frozen pattern of those waves, but the thickness of the layer softens the finest ripples while leaving the broader ones intact. That's why we still see strong, broad peaks in the CMB's pattern, yet the tiniest features are muted. Thickness also helps separate primordial imprints from later ones. After the fog cleared, forming galaxies and clusters could nudge CMB photons, either by gravitational tug or by scattering off hot gas, adding small secondary fingerprints. Because the last scattering layer has a known depth and timing, we can untangle much of this later post-production from the original image. The cleaner we model the layer, the better we can reconstruct what the young universe actually looked like. The sound horizon and BAO. Before the world became clear, matter and light were stuck together like a hot soup under a lot of pressure. Gravity pulled any tiny overdensity inward, which means there was a little more stuff in one place. But photon pressure pushed back, sending sound waves through the plasma. Around half the speed of light, those waves raced outward until the fog cleared, at which point they spread out. When light separated from the wavefronts, they stopped moving and froze in a certain radius. This radius was the farthest a sound wave could go before the world turned clear. That distance is the sound horizon, which is about 150 megaparsecs, or 500 million light-years in terms of how fast light moves. 2 fingerprints of this radius survive. The first is on the CMB itself, as the famous series of peaks in its temperature pattern, the acoustic peaks. The second, subtler one, appears billions of years later in the galaxy distribution, a small statistical excess of galaxy pairs separated by the sound horizon scale. This pattern is called Baryon acoustic oscillations, BAO. You won't see a visible ring in the sky. BAO is a statistical ripple, a tiny bump in the galaxy correlation function, or a wiggle in the power spectrum. But with enough galaxies, the signal stands out. What does BAO have to do with where the universe ends? Because the sound horizon is a standard ruler, a physical bar set by the physics of the early universe and perfectly tuned by the CMB. If you know how big the ruler really is, you can see how wide it looks in the sky at different redshifts, across the line of sight, and how stretched out it is along the line of sight as a whole. At that point in time, those two directions equal an angular diameter distance and a Hubble expansion rate. Putting these data together over cosmic time gives us a picture of the universe's shape and growth. This lets us test the past of acceleration and space curvature without making assumptions about the brightness of supernovae or how galaxies have changed over time. This is where galaxy redshift surveys earn their keep. By taking spectra of millions of galaxies, they convert angles on the sky into 3D positions and stack up the separations. The BAO bump is small, just a percent level enhancement at approximately 150 mpc. But it's clean because messy astrophysical details mostly average out across such large scales. Over time, gravity tries to smear the imprint as structures grow and galaxies move. But a technique called reconstruction uses the observed large-scale flows to reverse some of that blurring, sharpening the BAO ruler again. The power of BAO is consistency. The same early universe physics that set the CMB's acoustic peaks sets the late-time ruler in galaxies. When both agree on the sound horizon scale, we gain a cross-check that locks down distances and breaks key degeneracies in cosmological fits. That, in turn, narrows the allowed range of global curvature, how the universe bends on the largest scales, and constrains how the expansion rate evolves, critical inputs for any discussion of horizons and ends. A common question is whether BAO tells us where matter ends, for example, at the edge of a supercluster. It doesn't. BAO isn't a boundary like a shoreline. It's more like the faint echo of a drumbeat heard throughout the cosmos, subtly biasing where structures are more likely to form relative to one another. You'll find galaxies at all separations, but there's a slight preference to find pairs around the sound horizon distance, because many were born from shells of gas piled up by those ancient waves. One of BAO's strengths is that it can handle problems caused by astronomical phenomena. Stars and black holes giving and receiving feedback, changing the rate at which stars form, and mergers are all messy parts of galaxy creation, but they only have a small effect on big scales. When scales are very big, linear theory works well and normal behavior can be predicted, which is where the BAO scale fits in well. Systematics are kept in check, and BAO is now considered a top-level probe, along with supernovae, weak lensing, and cosmic chronometers. Epoch of reionization when the fog lifted. It was a long dark age after the cosmic microwave background freed photons. Matter cooled and clumped together, but there were no stars to light the way. After hundreds of millions of years, the first stars and black holes were born. Their strong ultraviolet light did more than just shine. It changed the medium itself by ripping electrons off of hydrogen atoms that were not charged. The epoch of reionization, EOR, is the slow, patchy change from a neutral universe to an ionized one. It is a real informational limit for astronomy. Before it, most ultraviolet light can't move far. After it, space becomes clear for those wavelengths and galaxies can be seen. Reionization didn't flip on like a light switch. It began with tiny islands of dawn. The earliest star clusters, possibly rich in massive, short-lived, metal-free stars, poured out ionizing photons that carved bubbles of hydrogen plasma around their host halos. As galaxies multiplied, bubbles grew, overlapped, and merged into ionized seas separated by shrinking pockets of neutral gas. Picture a cosmic foam, dark neutral cells thinning while bright, ionized regions connect into continent-sized patches. By about 1 billion years after the Big Bang, astronomers call this redshift, ZSIM-6. The last neutral strongholds gave way, and the intergalactic medium, IGM, was largely ionized. How do we know the timeline of cosmic reionization if we can't actually time travel? We rely on two key clues, quasars and the cosmic microwave background, CMB. Extremely bright quasars at very high redshift act like cosmic flashlights shining through the intergalactic medium. When astronomers look at their spectra, they see long dark gaps where neutral hydrogen has absorbed ultraviolet light. These absorption troughs reveal places where reionization was still incomplete. By the time we reach redshift Z6, those troughs largely disappear, showing that most of the hydrogen had become ionized by then. The second clue comes from the CMB's polarization. When free electrons reappeared during reionization, some CMB photons scattered off them one last time, leaving behind a faint but measurable polarization pattern across the sky. This signal tells us how many free electrons existed along our line of sight and helps date when reionization occurred. Putting both lines of evidence together, scientists conclude that reionization was not a sudden event but a gradual, uneven process that likely took place between redshift 10 and redshift 6, or roughly 500 million to 1 billion years after the Big Bang. Who did the heavy lifting? Galaxies or quasars? The consensus leans towards many small galaxies leaking a modest fraction of their ionizing photons into the IGM, rather than a few quasars doing it all. The math is simple in spirit. You need enough high-energy photons escaping star-forming regions to ionize each hydrogen atom and keep it ionized against recombination. Even faint, numerous dwarf galaxies can meet the budget if their escape fraction isn't too tiny. Quasars help, especially toward the end, but likely weren't abundant enough early on to dominate the whole process. The EOR reshaped what we can see. Neutral hydrogen is an effective curtain for ultraviolet light, so early galaxies were partly hidden until their local bubbles grew. This means our current galaxy counts at very high redshift are biased toward clear windows in the foam, regions where reionization ran ahead of schedule. It also means lines like Lyman alpha, a favorite tracer of young galaxies, flicker in and out of detectability depending on how much neutral gas sits between us and the source. When the cosmos finished reionizing, ultraviolet light could finally roam, and the large-scale cosmic web emerged in view. Why is the EOR still cloudy if it's so important? Because the devices we have now are already overworked. We can see the clearest views of the brightest early galaxies, but not the whole group of faint galaxies that likely powered reionization. That's why the 21 centimeter line given off by neutral hydrogen is such an important new message. In place of depending on a few beacons that shine through the fog, 21 cm observations offer a direct picture of the fog that shows where it stays neutral and where it's been charged, as well as how those areas grow and connect over time. To hear this hint, experiments like HERA and later the Square Kilometre Array were built. This turned the EOR from a guess into a movie. The cosmic neutrino background. Before photons could move around easily, and before there were even atoms, the universe was an ocean of quarks, electrons, neutrinos, and radiation that were all constantly interacting with each other. Something very important happened about 1 second after the Big Bang. Neutrinos stopped interacting with everything else. It looked like ghostly particles, with almost no mass and no charge, started to move through space, bringing a frozen record of that first moment. The universe is still full of that old radiation. The cosmic neutrino background, CNB, is its name. We have never directly found it, but its signs can be seen in many small ways. When the universe was less than a second old, it was so hot that neutrinos constantly collided with electrons and positrons, staying in thermal equilibrium. As space expanded and cooled below a few billion Kelvin, the collision rate dropped faster than the expansion rate. At that point, neutrinos effectively decoupled. They stopped scattering and began coasting freely through space-time, just as the cosmic microwave background photons would do hundreds of thousands of years later. But because they left so much earlier, their background is far colder and more diffuse today, with a predicted temperature of about 1.95 Kelvin. How can something so elusive matter to us? Despite being nearly undetectable, the CNB shaped the universe's expansion and structure. Each species of neutrino contributed to the total radiation density in the early universe, influencing how quickly space expanded. Faster expansion means that certain key events, like nucleosynthesis, the formation of light elements, and photon decoupling happened slightly sooner. Observations of the CMB and the abundance of helium and deuterium thus let us infer the presence of these early neutrinos indirectly. They act as an invisible hand in the timing of everything that follows. We even have a number for how much radiation these particles added. Cosmologists define an effective number of neutrino species, denoted nef-nef. The standard model predicts roughly 3.046, a tiny bit above 3, due to the details of particle interactions during decoupling. Measurements from the Planck satellite and other CMB experiments confirm that value within tight limits, reinforcing that the CMB really exists, even if no detector has yet felt a single one of its ancient neutrinos. Energy is what makes it so hard to find things. Each relic neutrino now only has a charge of about a 10,000th of an electron volt. They are so weak that regular detectors can't pick them up. Light years of lead don't bother them at all as they pass through it. The most popular idea for direct viewing is to use tritium that is very cold. The goal of the Ptolemy project is to catch neutrinos using a unique reaction. When a spent neutrino interacts with a tritium nucleus, it can cause beta decay just above the normal energy barrier. Finding that tiny extra would prove that the CMB exists. We would be able to touch the first second of cosmic history if we were able to complete this very tough test. Even without direct detection, the CMB's influence reaches into modern cosmology. Neutrinos, though light, are not massless. As the universe cooled, they transitioned from behaving like radiation to behaving like a dilute form of matter that drifts too fast to clump on small scales. This free streaming smooths out the fine-grained structure of galaxies and clusters. The amount of that smoothing depends on their total mass. So by studying the clustering of galaxies and the CMB lensing pattern, scientists can place upper limits on neutrino mass, essentially weighing particles we can't see by the way they sculpt the cosmic web. There is another kind of boundary that the CMB describes. It is the neutrino last scattering surface, which is much older and farther away in time than the photon one. Its formation marks the oldest time period from which any known particle has kept a record of the surroundings. If we could map the CMB, we'd see the universe less than 2 seconds old, which is 1 billion times younger than the view from the CMB. That would give us a whole new way to look at how energy and matter first got sorted, how differences between matter and antimatter became permanent, and how basic forces acted before the growth of the universe slowed down enough for atoms to form. Primordial gravitational waves. Before there was light, atoms, or even neutrinos that weren't connected to each other, the universe may have been vibrating with waves of gravity moving through space-time. These waves weren't made by black holes or stars. Instead, they were made by very fast, violent events in the very first few seconds after the Big Bang. If found, they would carry data from the oldest time that we can access in the universe, which is much further back than any photon or particle. For the most part, they are nature's greatest time vault. Gravitational waves are distortions in the fabric of space-time that travel at the speed of light. Unlike ordinary matter or radiation, they don't scatter or absorb easily, which means they pass almost untouched through anything, including the hot, dense plasma of the early cosmos. That's why cosmologists chase them. While light from before the cosmic microwave background is blocked by the opaque early universe, gravitational waves would have slipped through effortlessly, preserving a pristine record of whatever stirred them. The most promising source of these primordial signals is cosmic inflation, a brief, explosive expansion that likely happened within the first 10 to the power of minus 34 seconds after the Big Bang. During this instant, tiny quantum fluctuations in space-time were stretched to cosmic sizes, creating ripples known as gravitational waves that spread across the universe. These ancient waves still exist today, gently distorting space-time everywhere, but they're far too weak for our current instruments to detect directly. Instead, scientists search for their fingerprints, subtle imprints these waves may have left on other cosmic signals. such as the polarization patterns in the cosmic microwave background. The best-known imprint would appear in the polarization pattern of the CMB. Ordinary density fluctuations create a smooth, curl-free polarization, the so-called E modes, but gravitational waves produce a twist, a distinctive B mode pattern, tiny spirals in the polarization map. Detecting that swirl would be strong evidence for an inflationary gravitational wave background. Experiments like BICEP, Keck-Array, and the upcoming LightBird satellite aim to measure polarization with the sensitivity needed to separate that signal from foreground dust and lensing effects. So far, the search has yielded upper limits, but every improvement tightens our understanding of how energetic the universe's birth could have been. Gravitational waves also come from other early universe phenomena. Some theories predict phase transitions, moments when fundamental forces change their character, like water freezing into ice but in energy fields instead of molecules. If such transitions were violent enough, they could generate bursts of gravitational waves across a range of frequencies. Likewise, hypothetical objects called cosmic strings, thin defects in spacetime left over from the early universe, could repeatedly snap and reconnect, radiating powerful waves. Unlike the inflationary background, these would show up as a continuous hum or occasional bursts in future space-based detectors. To catch these signals, astronomers are building a new generation of instruments that listen to spacetime itself. Ground-based interferometers like LIGO, Virgo, and CAGRA already detect waves from merging black holes and neutron stars, but primordial waves are far weaker and longer in wavelength. For those, space missions such as LISA, Laser Interferometer Space Antenna, will use million-kilometer baselines to probe lower frequencies. Even longer wavelengths can be tracked by pulsar timing arrays, which look for correlated timing variations across dozens of pulsars. Recently, hints of a stochastic gravitational wave background have emerged from these arrays, possibly from ancient cosmic sources or from merging supermassive black holes. But inflation remains a tempting alternative explanation. Spatial curvature, flat, open, or closed. Next, we need to figure out what shape the universe is. This is because we have already mapped the cosmic background and found its first waves. Is space smooth like a sheet that never ends, curved like a saddle, or curved like the sphere's surface? The answer tells us not only how big the universe is, but also if it has an edge that we could ever reach or not. In cosmology, curvature doesn't mean local bumps or dips caused by stars or black holes. It's about the overall geometry of space when you average across billions of light years. General relativity allows three broad possibilities. If the universe's total density equals a special critical value, space is flat, parallel lines never meet, and triangles add up to 180 degrees. If the density is higher than critical, space is closed and positively curved, like a three-dimensional sphere. If it's lower, space is open and negatively curved, like a saddle stretching to infinity. This isn't an abstract idea, it's testable. The key lies in how light travels across curved space. Imagine a fixed physical ruler placed at a known distance. In a closed universe, light paths bend inward, making the ruler appear larger in the sky. In an open universe, paths bend outward, making it appear smaller. In a flat universe, geometry behaves just like our everyday intuition. The cosmic microwave background provides an ideal test. The sound horizon imprinted in its hot and cold pattern is a known physical scale. By measuring its angular size on the sky, we can infer the geometry that projects that scale onto our view. When the Planck satellite and other experiments mapped the CMB with exquisite precision, they found that the first acoustic peak in the power spectrum sits almost exactly where a flat universe predicts. The allowed deviation from perfect flatness is tiny, less than about 1 part in 100. That means, to the limits of observation, space is remarkably flat. If it's curved at all, the radius of curvature is far larger than our observable universe, so we'd never notice the bend from inside our small patch. Flatness, however, raises a puzzle known as the flatness problem. If the universe has been expanding for billions of years, any initial curvature would have grown over time, like a small dent inflating into a huge bulge. To stay as flat as it is today, the early universe must have started unimaginably close to flatness, unless something actively drove it that way. That something is one of the main motivations for the theory of inflation, a brief period of exponential expansion that stretches any pre-existing curvature smooth, leaving the cosmos effectively flat on large scales. However, flat doesn't always mean infinite. Even if the universe is flat, it could still curve around itself in strange ways, like how a video game screen loops when you walk off of one end. This is what mathematicians call topology. If the structure of the universe is small, light could theoretically go all the way around and come back from the other direction, making patterns or matched circles in the CMB. Scientists have looked for these kinds of patterns, but none have been found yet. That means the loop size is bigger than the part we can see if space does wrap. Measurements beyond the CMB also weigh in. Large-scale galaxy surveys, baryon acoustic oscillations, and gravitational lensing maps all confirm the same near-flat geometry. Together, they give us a consistent picture. Within the observable universe, space behaves like a Euclidean stage. This agreement across different methods strengthens the case that curvature, if present at all, is extremely small. Why does curvature matter for where the universe ends? Because the shape dictates its global extent. An open universe expands forever, stretching distances endlessly without ever looping back. A closed universe is finite but unbounded. You could, in theory, travel in one direction indefinitely and end up where you started, without ever finding an edge. A flat, infinite universe has no boundary at all. It just continues without limit. In none of these cases is there a physical wall or border to hit, just different ways geometry wraps or stretches the fabric of space. Cosmic topology. Could space wrap around itself? It's not always true that the world is endless, even if it is geometrically flat. One way to think about space is as a cosmic version of a video game map that loops when you cross an edge. This idea is known as cosmic topology, and it doesn't look at the shape of the universe on a small scale. That's a curve. Instead, it looks at how space ties to itself on a large scale. In other words, would you end up back where you started if you could go far enough in one direction? Think of a two-dimensional analogy. On a flat piece of paper, you can draw straight lines forever without looping around. But take that same sheet, roll it into a cylinder, and suddenly one direction closes on itself while the other remains infinite. Connect the ends again to make a torus, a donut shape, and now both directions loop. The surface is finite, yet has no edges. In 3 dimensions, the same principle applies. Space could be topologically compact even if its curvature is 0. Mathematically, there are dozens of possible 3D wraparound configurations, each defining how space repeats. If space does loop, light from distant galaxies could take multiple routes to reach us. That means we might see duplicate images of the same object at different positions and redshifts. On the larger scales, we could even see repeated patterns in the cosmic microwave background, CMB, where light from the same patch of the early universe circles around the cosmos and enters our telescopes from different directions. These potential repetitions are known as circles in the sky. Cosmologists have spent years searching for such circles using CMB data from the WMAP and Planck missions. The idea is simple. Match up temperature patterns along circles in opposite directions. If the universe loops around within the radius of the observable universe, those circles would line up nearly perfectly. So far, the results show no clear matches. That tells us that if space does wrap around, the loop size must be larger than our observable region, probably at least several times larger than the 93 billion light-year diameter we can currently see. There are also other ways to test cosmic topology. Large-scale galaxy surveys could, in theory, reveal repeated structures, identical clusters or filaments appearing in different parts of the sky. Gravitational waves might echo in similar ways. passing through the same region more than once if space connects back on itself. But all of these methods face the same challenge. The universe is expanding, and cosmic structures evolve over time. Even if two light paths start from the same object, billions of years of cosmic change can make their images look completely different by the time they arrive. Still, topology leaves behind small marks. Some big changes in the CMB would be slowed down by a compact universe. This is because only certain wave modes can fit nicely into the limited area, like standing waves on a drum. Planck's readings do show that the sky's biggest temperature modes are not as strong as thought. That could just be a cosmic accident, but it leaves the door open for a small but limited topology, maybe one that is just beyond what we can see. Comoving versus proper distance. There are different ways for cosmologists to talk about how far away something is. In a world that is growing, the idea of distance changes shape all the time. There is no one constant measure that works for all situations. The difference between comoving distance and proper distance is what makes it possible for numbers like 46 billion light-years for the edge of the visible universe and a cosmic age of only 13.8 billion years to exist at the same time. Start with proper distance. Imagine pausing cosmic expansion for an instant, freezing the stretching of space, and then measuring the gap between you and a distant galaxy with a ruler at that moment. That instantaneous separation is the proper distance. But because the universe expands, this number changes over time. Galaxies farther away are being carried along by the Hubble flow, so their proper distance grows even though they aren't moving through space in the usual sense. Co-moving distance takes a different perspective. It removes the expansion factor and measures how far 2 points are apart in coordinates that expand with the universe. In comoving terms, galaxies that simply follow the general expansion keep the same coordinate distance forever. It's like marking 2 spots on a rubber band and labeling their positions in centimeters on the original unstretched band. As the band stretches, their coordinate positions don't change, even though the actual gap grows. Comoving distance lets cosmologists describe where things are in a way that isn't constantly shifting with time. When astronomers say the observable universe has a radius of about 46 billion light-years, they mean comoving distance, the separation those regions would have today if we could freeze expansion and lay out rulers. The look-back time, about 13.8 billion years, refers to how long the light from those regions has been traveling to us. During that time, space itself stretched, carrying the emitting galaxies much farther away than the light travel time alone would suggest. The same journey, described with proper distances at different epochs, yields different numbers at every step. These two measures become especially useful when plotting light cones. A photon travels on a 45-degree line in a space-time diagram only if we use co-moving coordinates scaled by the universe's expansion. That's why cosmologists often describe horizons and limits in co-moving distances. They're fixed coordinates that don't expand while you're watching. Proper distances, in contrast, are what an observer would measure now if they could instantly teleport to the object and pull out a ruler. Different types of distance fill out the same picture. Angular diameter distance relates an object's actual size to how large it appears in the sky. Luminosity distance relates its true brightness to how dim it looks due to expansion and redshift. Both are derived from the same comoving framework, but include the stretching and dimming effects of cosmic expansion in different ways. That's why distant galaxies can appear surprisingly large at certain redshifts. Geometry, not illusion, makes that happen. Many paradoxes in the universe can also be explained by knowing what distance you're using. For instance, if the universe is only 13.8 billion years old, how can galaxies move away faster than light? Because the speed of decline is based on how the proper distance changes over time, and the proper distance changes because space is stretched, not because of motion through space. It's not the galaxies that go faster than the local speed limit, it's metric expansion that moves them farther apart faster than photons can close the gap. The future event horizon in a dark energy universe. We can see how far into the past the particle horizon tells us. The event horizon tells us how far into the future we can see. It's the very edge of the universe, not a wall or a limit in space, but a limit in time and fate. What's even stranger is that dark energy means that most of the world will soon be out of our reach forever. Consider shooting a beam of light right now to a galaxy far away. If the world were made of only matter, that light might get there in the end, but it might take a very long time. But in our universe, which is ruled by dark energy, the mystery force speeding up the expansion of the universe, space grows so fast that no signal we send today will ever be able to catch up. In the opposite direction, no matter how long we wait, light from galaxies that far away will never reach us. The cosmic event horizon is set by that limit. Calculations based on current cosmological parameters put that horizon's radius at about 16 billion light-years in proper distance today. Anything farther away is already lost to us, not because it has disappeared, but because the space between us is expanding faster than light can traverse it. Even galaxies still visible now, whose light left them billions of years ago, are quietly drifting beyond that horizon as we speak. Their photons are en route, but once the last ones arrive, no new information will ever follow. It's a mind-bending situation. The universe keeps expanding, yet the observable part shrinks in practical terms. Every passing billion years, more galaxies vanish from view, not by fading or moving behind an obstacle, but because their light can no longer overcome the swelling of space. Eventually, only our local group, the Milky Way, Andromeda, and a handful of satellites, will remain gravitationally bound. Everything else will have crossed the event horizon, carried outward into a darkness from which no future message can return. This behavior is described by what physicists call a de Sitter universe, one dominated entirely by dark energy. In such a cosmos, the expansion rate approaches a constant value, and the event horizon becomes a fixed boundary. It's somewhat like the horizon around a black hole, an invisible limit beyond which events can never affect an observer. The difference is scale. For a black hole, the horizon traps light inside. For the universe, it traps light outside. Both represent the same principle, regions of space-time separated forever by expansion. This horizon isn't static in human terms. As time goes on, galaxies near the edge redshift more and more strongly. Their light stretches to longer wavelengths, growing dimmer and colder until it's undetectable. Even before crossing the horizon, they effectively fade from existence to any telescope. Over trillions of years, the night sky will empty out. The CMB will cool toward absolute zero, and intergalactic communication will become physically impossible. The universe won't end in fire or collapse, but in silence, each island of gravity, cut off in its own private bubble of space. We can see how young the universe is when we look far into space, but we can also see how it will be in the future, since those faraway galaxies are already too far away to be affected by anything we do. The last light we'll ever get is from them. There is no event horizon at the edge of what we can see now. Instead, it is just beyond what we can see, marking what we'll never see again. For scientists, the event horizon isn't just a curiosity. It shapes how we think about the ultimate fate of information. In principle, any process or signal occurring beyond that horizon will never influence our region of space. It might as well be erased from our cosmic record. Whether dark energy remains constant or changes over time will decide how this boundary evolves. If the energy density grows stronger, the horizon shrinks closer. If it weakens, the horizon may drift outward or vanish altogether. The GZK cutoff, the cosmic ray horizon. The universe already had a way to reach us, billions of light years away, long before there were space telescopes and radio arrays. It sent us cosmic rays. These tiny particles, mostly protons and atomic nuclei, are sped up to impossible speeds by powerful cosmic engines like supernovae, active galactic nuclei, or even things we haven't even found yet. So close do the fastest ones move to the speed of light that one proton has as much energy as a baseball thrown at full speed. But even these very adventurous tourists can only go so far. When they get too far away, the universe slows them down. That limit is known as the GZK cutoff, after Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, who all predicted the effect in the 1960s. It describes a natural energy ceiling for cosmic rays traveling through intergalactic space. The reason is surprisingly simple. The universe is filled with a thin fog of leftover radiation, the cosmic microwave background, CMB. These low-energy photons have been drifting since the universe was about 380,000 years old, and they fill every cubic centimeter of space. When an ultra-high-energy cosmic ray plows through that fog, it occasionally collides with one of those photons. In the particle's own frame, the encounter looks like smashing into a wall of gamma rays. Each collision robs it of energy, step by step, until it can no longer maintain its extreme speed. This process means there's a horizon for cosmic rays much like the one for light. Any proton with an energy above about 50 quintillion electron volts cannot travel more than roughly 100 million light-years before losing too much energy to continue as a truly ultra-high energy cosmic ray. That may sound enormous, but it's tiny compared with the 46 billion light-year radius of the observable universe. Beyond that distance, cosmic rays fade long before they reach us, effectively limiting the size of the cosmic neighborhood that can send such particles our way. Astronomers have seen this limit in action. In the early 2000s, observatories like the Hayes detector in Utah and the Pierre Auger Observatory in Argentina noticed that the number of detected particles drops sharply above that predicted energy threshold. This drop wasn't an instrumental glitch, it was the universe itself enforcing its speed limit. The results confirmed that the CMB is not just a relic of the Big Bang, but also a barrier, setting a maximum reach for the most energetic particles known. What does this tell us about cosmic geography? It means the sources of the highest energy cosmic rays must lie nearby in astronomical terms, within a few hundred million light-years at most. That narrows the search to a small subset of potential accelerators, the jets of nearby active galaxies, shock waves in galaxy clusters, or perhaps young, powerful neutron stars. So far, no single class of object has been proven guilty, but the patterns of arrival directions hint that these particles are tracing the large-scale structure of the local universe, filaments, voids, and magnetic fields that weave between the galaxies we can see. Cosmic rays don't fly straight like light beams. They are charged, and the magnetic fields that thread through space bend their paths. By the time one reaches Earth, its original direction can be deflected by several degrees or even completely scrambled, making it almost impossible to point back to its birthplace. The combination of the GZK cutoff and magnetic deflection means that even if something extraordinary is hurling particles our way from the edge of the cosmos, we'll never know. The universe filters and reroutes the evidence before it arrives. Gamma ray, attenuation, and the extragalactic background light. Light has its own limits in the vastness of space. You might think that photons, which are light, fast, and can't be stopped, can travel through the world without any problems, but even light runs into trouble. As high-energy gamma rays travel through space, they slowly lose their freedom as they hit the soft glow of older stars that are spread out between galaxies. This quiet exchange makes a gamma ray barrier, which is a line beyond which the brightest light can't reach us. Between galaxies, space isn't dark. It's filled with the faint relic of everything that has ever shone. Ultraviolet, visible, and infrared light from all past generations of stars and dust. Collectively, this diffuse radiation is called the extragalactic background light, or EBL. To our eyes, it's invisible, drowned out by closer sources, but for a gamma-ray photon racing across millions of light-years, the EBL is a minefield. When a very energetic gamma-ray meets one of those faint background photons head-on, the collision can transform both into an electron-positron pair. This process annihilates the gamma-ray, effectively removing it from the cosmic record. The higher the photon's energy, the shorter the distance it can travel before such a collision occurs. For gamma rays with energies around a few 100 billion electron volts, the universe becomes opaque beyond a few billion light-years. For photons in the trillion electron volt range, the cutoff distance is only a few 100 million light-years, similar to the GZK horizon for ultra-high energy cosmic rays. That means the most powerful gamma rays we detect must come from nearby sources, close active galaxies, blazars, or supernova remnants in our cosmic neighborhood. Anything farther away is dimmed, blurred, or erased before its photons ever arrive. This loss of light doesn't just block our view, it also tells us about the past of light. Astronomers can figure out the EBL by measuring how the brightness of gamma ray sources drops with distance. This lets them figure out how much starlight and dust emission there is in the universe and when it was made. This way of mapping has been used by satellites like Fermi and ground-based telescopes like HESS, MAGIC and Veritas to show how the cosmic light background has changed over billions of years. Based on what they found, the EBL was strongest when the universe was about 3 billion years old, when stars were being formed at the fastest rate. The background has slowly faded since then, as galaxies have aged and slowed down the formation of stars. Gamma-ray attenuation also shapes how we interpret cosmic explosions. Blazars, galaxies with supermassive black holes shooting jets of plasma directly toward us, emit enormous bursts of gamma radiation. But the farther away a blazar is, the more its gamma rays are absorbed by the EBL, leaving us only a softened spectrum. Without accounting for this cosmic fog, we'd underestimate how energetic those sources truly are. Even more extreme events like gamma-ray bursts must fight the same battle. The higher their energy, the harder it is for their light to make it here intact. This light-eats-light interaction gives the universe a practical edge for photons. Beyond a certain energy, no telescope, no matter how sensitive, will ever detect sources past the gamma-ray horizon. For astronomers, that horizon sits roughly at a redshift of 1 for the highest energies currently observed. The intergalactic medium and the Lyman alpha forest. There is a place between galaxies that is neither empty nor quiet. It is called the intergalactic medium, or IGM, and it is made up of a huge, unstable ocean of gas. Even though it's hard to see, it makes up most of the standard matter in the world. The IGM is where galaxies get new fuel and throw out enriched matter. It's also where the cosmic web, the big structure of the universe, gets its strands and holes. It's also where light from faraway galaxies and quasars gets bent and damaged, leaving behind the Lyman alpha forest, one of the most beautiful signs in astronomy. The IGM is mostly hydrogen, with a touch of helium and trace elements. Although it's thinner than the best vacuum ever made on Earth, it stretches across the spaces between galaxies, filling filaments that connect galaxy clusters and enclosing immense voids. After reionization, most of this gas became ionized, meaning its electrons were stripped away by the ultraviolet radiation of stars and quasars. But small fluctuations in density and temperature remain, creating tiny clouds or filaments of neutral hydrogen sprinkled through the ionized medium. These thin patches are what create the Lyman alpha forest. Here's how it works. Distant quasars, hyperactive galactic nuclei powered by supermassive black holes, shine brightly across billions of light-years. As their light travels to us, it passes through countless pockets of hydrogen. Each time it encounters a region dense enough to contain some neutral hydrogen, that gas absorbs light at a very specific wavelength, corresponding to hydrogen's Lyman alpha transition, about 121.6 nanometers in the ultraviolet. But because the universe is expanding, each cloud is moving away from us at a slightly different velocity, which shifts the absorption to a slightly different wavelength. The result is not one absorption line, but hundreds, forming a forest of dark, narrow lines across the quasar's spectrum. Each of those tiny absorption dips marks a different structure along the line of sight, like mile markers stretching across billions of years. By analyzing their distribution, scientists can map the density fluctuations of the universe at intermediate scales, between the largest galaxy clusters and the smallest galaxies. The Lyman alpha forest therefore acts as a 3D chart of the intergalactic medium, showing where gas is dense, where it's thin, and how it flows under the pull of gravity. Arguably, the most amazing thing that has been discovered from this method is how organized the universe is, even though it seems empty. Simulations said that the IGM would follow the shape of the cosmic web, which is made up of long strands that feed galaxies and clusters and huge, bubble-like gaps in between. Astronomers can even figure out the 3D shapes of these filaments, an unseen web of matter that spans hundreds of millions of light years, by comparing the patterns of absorption across different quasar sight lines. The Lyman alpha forest also helps test cosmological models. Because the gas follows dark matter's gravitational potential, its fluctuations encode information about the universe's overall matter content, expansion rate, and the nature of dark matter itself. Warm dark matter, for instance, would smooth out small-scale structure, thinning the forest's fine detail. Comparing simulations with observed spectra lets scientists rule out or refine those possibilities. The forest gives clues about the temperature history of the universe. The width of each absorption line reflects the thermal motion of hydrogen atoms. Hotter regions produce broader lines. After reionization, ultraviolet light from galaxies and quasars reheated the IGM, and it has been cooling ever since. Measuring how the average temperature changes with redshift tells us when reionization ended and how intense early starlight was. Beyond mapping structure, the Lyman alpha forest reveals how baryons, the normal matter of the universe, are distributed. For decades, cosmologists noticed a discrepancy. Galaxies and hot clusters contained only about half the baryons predicted by Big Bang nucleosynthesis. The forest helped solve that puzzle by showing that the missing matter wasn't gone. It was hiding as thin, warm plasma spread throughout intergalactic space. Though delicate and invisible, the IGM shapes nearly everything we see. Galaxies form where it collapses, quasars light up when it falls into black holes, and its absorption fingerprints let us trace the large-scale flow of matter itself. The Lyman alpha forest, in effect, is the universe's barcode, encoding billions of years of growth in thin black lines across the light of quasars. Virial radii and the edges of dark matter halos. Dark matter surrounds every galaxy and every group of galaxies, but we can't see it. These halos go far beyond the stars and gas that can be seen. They show how big each system really is and how far its gravity can pull things together. But where does the end of a halo really lie? As an answer, astronomers use the virial radius, a line that divides matter that is still held in place by gravity from the flow of the universe moving outward. The concept comes from the virial theorem, which relates a system's average kinetic energy to its gravitational binding energy. In simple terms, inside the virial radius, gravity wins. Particles and gas are moving fast, but not fast enough to escape. Beyond that radius, cosmic expansion dominates, pulling matter away faster than the system can reel it back. So the virial radius marks the region where a halo has settled into equilibrium, no longer collapsing, but not dissolving either. For a typical galaxy like the Milky Way, the virial radius is about 250,000 to 300,000 light-years, roughly 10 times larger than the visible disk of stars. The Milky Way's dark halo contains around 1 trillion times the mass of the Sun, most of it unseen. Inside that radius, stars orbit stably, gas clouds swirl, and satellite galaxies remain bound. Outside it, the density drops rapidly, blending into the intergalactic medium and the general expansion of the universe. Clusters of galaxies push this idea to an even grander scale. A rich cluster can have a virial radius of 5 to 10 million light-years, enclosing hundreds or even thousands of galaxies, plus vast amounts of hot X-ray emitting gas. The gas temperature and galaxy speeds both provide independent checks. Inside the virial boundary, their motions are roughly balanced by the cluster's gravity. Beyond it, galaxy velocities start to follow the universal Hubble flow instead of orbiting the cluster's center. Defining the virial radius precisely depends on the cosmological context. Astronomers often express it using a number called R200, the radius within which the average density is 200 times higher than the cosmic mean. That factor isn't sacred. It's chosen because simulations show that halos roughly settle into equilibrium around that density contrast. Different conventions, R500, RVIR, etc., simply use slightly different thresholds, but the underlying idea remains the same. Inside, gravity dominates. Outside, expansion wins. Observations confirm that halos have no sharp edge. Instead, their density profiles decline smoothly, usually following a universal form known as the Navarro-Frenk-White profile, dense near the center, gently tapering off at larger radii. The edge we draw is a useful approximation, not a physical cliff. Still, it's an important one. It defines how much mass a galaxy or cluster really contains, and sets the stage for everything from star formation to gravitational lensing strength. Recent studies using weak gravitational lensing, subtle distortions in the shapes of background galaxies, allow us to measure these halos far beyond where we can see stars or gas. The results show that halos overlap and blend into one another, connecting through the cosmic web's filaments. In that sense, there's no empty gap between galaxies, only gradual transitions where one halo's influence fades and another begins. For our own galaxy, the virial boundary also defines what's gravitationally ours. The Magellanic Clouds, for example, orbit well within the Milky Way's halo and will eventually merge with it. The more distant Andromeda Galaxy, about 2.5 million light-years away, sits within its own halo. The two halos are already touching, a quiet prelude to the eventual Milky Way-Andromeda merger several billion years from now. Beyond their combined reach lies the edge of the local group, where the expansion of the universe starts to overcome local gravity. The local group's turnaround radius. There is a point past which gravity can no longer hold on to any system that is gravitationally bound, whether it is a planet orbiting a star orbiting a galaxy, or a galaxy orbiting within a cluster. In the area around our galaxy, that line we can't see is called the turnaround radius. It shows where the pull of the local group's gravity equalizes with the push of the growth of the universe. Within that line, galaxies fall toward each other because they are pulled together by gravity. Beyond it, space grows faster than their pull can pull it back. There is a real line there between what will always be our cosmic island and what will drift off into the great beyond. Consider thinking about the local group, which is made up of about 50 galaxies led by the Milky Way and Andromeda, M31. A gravitational dance is going on between them that will finally cause them to join, making one huge elliptical galaxy in a few billion years. The Magellanic Clouds, the Triangulum Galaxy, M33, and dozens of dwarf partners are just a few of the smaller systems that circle around these two main players. They have about 4 to 5 trillion suns worth of mass, and most of it is dark matter. All of these galaxies move around in the same sphere, which is about 3 million light-years across. The turnaround radius lies just beyond that, at around 3 to 4 million light-years from the center of mass of the local group. At this distance, the average outward motion of galaxies relative to the group switches sign. Inside, galaxies are being pulled inward or orbiting. Outside, they're receding with the Hubble expansion. Observationally, astronomers identify this boundary by measuring galaxy velocities in our local volume. Systems like the nearby Leo 1 group or the Sculptor group sit close to this limit, right on the edge where expansion begins to dominate. This boundary isn't fixed forever. It evolves with cosmic time. In the early universe, when expansion was slower and matter was denser, gravitational regions could grow larger as they pulled in surrounding material. But now, as dark energy accelerates the expansion, the cosmic tug-of-war is tilting in the opposite direction. Gravitationally bound regions can no longer expand indefinitely. The turnaround radius for each structure effectively marks its maximum size, the largest reach its gravity will ever have. Beyond that, the Hubble flow wins for good. Simulations show that over the next tens of billions of years, the local group will merge into a single galaxy surrounded by a vast, dark halo, but its turnaround radius will remain roughly stable. Every more distant galaxy will continue to recede beyond reach. Eventually, the local group will become a self-contained island adrift in an ever-emptier universe. Future observers, if any still exist, will see nothing beyond their merged galaxy's faint halo and a dark sky devoid of external galaxies. To them, the observable universe will have shrunk to a single, bound world. The turnaround radius concept extends beyond our neighborhood. Clusters like Virgo, Coma, and Perseus Pisces each have their own turnaround boundaries, defining the region that will stay gravitationally intact, while everything beyond drifts away. Collectively, these basins of attraction carve the universe into a mosaic of future islands. In a sense, the cosmic web we see today is temporary. Expansion will stretch the filaments thinner, and each cluster's turnaround radius will isolate it as a separate universe of its own. Finding these limits isn't just a matter of keeping track of the universe's money, it's a test of the gravity rules themselves. In some different theories of gravity, the point where pull and cosmic acceleration meet changes, which changes the size of the predicted turn. Astronomers can find out if dark energy acts exactly like Einstein's cosmological constant, or if it does something more strange by comparing the speeds of galaxies that have been seen to those that have been predicted. The cosmic web, filaments, nodes, and voids. When we look at the world as a whole, galaxies are not spread out in a random way. They make a cosmic web, which is a huge structure made up of filaments, dense knots, and gaps, which are huge empty areas. It's the real structure of the universe, a three-dimensional web that spans hundreds of millions of light-years. The bright threads we see in scans of galaxies are only the brightest parts of a much denser structure made up of dark matter, gas, and old gravity flows. This web began as tiny density ripples in the early universe, subtle fluctuations recorded in the cosmic microwave background. Over billions of years, gravity amplified those ripples. Matter flowed from low-density regions into higher ones, forming long filaments and dense intersections where galaxies and clusters grew. Simulations like the famous Millennium Run or Illustris show this process vividly. Small clumps merge into strands, strands braid into sheets, and sheets meet at thick nodes. The result looks uncannily like a living network of neurons, or the veins of a cosmic organism. The filaments are the highways of the cosmos. They contain most of the universe's matter, both visible and dark, funneled along gravitational gradients toward clusters and superclusters. Hot, diffuse gas fills these structures, often at temperatures of millions of degrees, so thin that it's invisible to optical telescopes but detectable in X-rays or through faint distortions in the cosmic microwave background. The regions where filaments intersect form nodes, the densest areas of the web, where massive clusters of galaxies like Coma or Virgo reside. These nodes are gravitational anchors, slowly accreting material from surrounding filaments, even as cosmic expansion tries to pull everything apart. Between the filaments lie the voids, enormous bubbles of near-empty space that can span tens to hundreds of millions of light-years. They're not entirely empty, just sparsely populated with small, faint galaxies. Voids are crucial for understanding cosmic evolution because they expand faster than the average universe. With little matter inside to slow them down, they act as pressure valves for the cosmic web, growing larger and rounder with time while filaments stretch thinner between them. The cosmic web's existence was confirmed dramatically in the 1980s and 1990s when surveys like the CFA Redshift survey and later the Sloan Digital Sky Survey, SDSS, mapped tens of thousands of galaxies in 3D. What emerged wasn't a smooth cloud, but a lacework of chains and hollows, the Great Wall, Sloan Great Wall, and Buta's Void among the most striking features. The Great Wall alone spans more than 500 million light-years, a sheet of galaxies so large that early astronomers doubted it could exist without breaking the assumptions of cosmology. But simulations soon showed that such structures are natural outcomes of gravitational growth on a cosmic scale. On smaller scales, the web continues down to the level of individual halos. Galaxy groups connect along thin bridges of dark matter, sometimes traced by faint streams of hot gas or even intergalactic light stripped from galaxies during encounters. These filaments feed galaxies with new material, driving star formation and growth. In this sense, the cosmic web isn't static. It's the circulatory system of the universe, moving matter and energy between its nodes like blood through arteries. Studying the web has become one of cosmology's most powerful tools. By analyzing the shapes and alignments of filaments, scientists can measure how structure growth depends on dark matter and dark energy. The web's geometry reflects the balance between gravity's pull and the universe's expansion. If dark energy was stronger or weaker, the filament's thickness, alignment, and clustering would look different. Even the voids help. Because they expand faster than average, their shapes provide sensitive tests of cosmic acceleration and the laws of gravity. Galaxy clusters and the splashback radius. Galaxy clusters are the biggest gravity cities in the universe. They are where strands of dark matter and gas meet in the middle of the cosmic web. There are hundreds to thousands of galaxies in each cluster, as well as huge clouds of superheated gas that glow in X-rays, and an even bigger pool of dark matter that holds everything together. Astronomers used to think that clusters slowly faded into space between galaxies. But new research shows that there is something sharper at the edge. It's a physical limit called the splashback radius. This is where matter coming in literally hits its turning point and splashes back outward before settling into orbit. Galaxies and dark matter constantly fall toward a cluster under its immense gravity, drawn in along the cosmic filaments. As they plunge inward, they accelerate to enormous speeds, often thousands of kilometers per second. When they reach the dense core, tidal forces and the hot intracluster gas slow them down. Some pass through and continue outward again before being pulled back in, tracing elongated orbits. The outermost point of those first orbits, the farthest they reach before falling inward again, marks the splashback radius. Beyond it, galaxies are still on their first infall. Inside it, they've already orbited at least once. You can think of the splashback boundary as the real edge of a cluster's halo. Inside, material is mixed and virialized. Outside, it's still streaming in for the first time. In simulations, the transition shows up as a sharp drop in density, sharper than anywhere else in the halo profile. Observationally, this feature has been detected using large optical surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, which measure how the number of galaxies changes with distance from a cluster's center. Around the splashback radius, the galaxy count suddenly plunges, confirming the predicted boundary. The finding isn't just noteworthy, it changes how we think about the real size of a cluster. The virial radius, which is based on the idea that the average density is a certain multiple of the universal mean, is not always a good way to measure things. In comparison, the splashback radius comes straight from dynamics, or how things move when they are pushed by gravity. It tells us how long ago the cluster grew and how fast new stuff is adding to it. A cluster that is constantly feeding on filaments around it tends to have a smaller splashback radius because matter dropping into it moves faster and goes deeper before turning around. A less tense cluster has a bigger one. This dynamic boundary also offers a new test of dark matter physics and cosmic expansion. If gravity behaves differently on large scales, or if dark energy alters how structure forms, the location of the splashback feature shifts. By comparing many clusters at different redshifts, astronomers can trace how quickly the universe's largest structures are assembling today versus in the past. The results so far match the predictions of standard cosmology remarkably well. Clusters are still growing, but at a slowing pace as dark energy takes over. Inside the splashback radius, clusters are among the hottest and most extreme environments in the universe. Gas temperatures reach tens of millions of degrees, creating X-ray halos visible to observatories like Chandra and XM Newton. Fast-moving galaxies ram through this gas, leaving glowing trails as their own interstellar material is stripped away by ram pressure. These processes quench star formation, transform spiral galaxies into featureless ellipticals, and fill the cluster core with old red galaxies orbiting like embers in a furnace. Once you get past the splashback, the story changes. Here, galaxies are still falling in, their shapes still intact and their gas tanks full. There are a lot of spirals that are changing because new people are joining the crowded cluster setting for the first time. Filaments bring new galaxies and gas to the edges of the cluster, which keeps its slow growth going even as cosmic acceleration starts to stop new material from coming in. Ram pressure and tidal boundaries. Not every galaxy that joins a cluster stays whole. It is hit by unseen forces that change it forever as soon as it crosses that dense, rough world. Ram pressure and tidal stripping are two of the biggest. They shape the area where a galaxy really ends. They set records not for distance or density, but for how long someone could keep going. Ram pressure works like a cosmic headwind. As a galaxy plunges through the superheated gas filling a cluster, the intra-cluster medium, it encounters particles moving thousands of kilometers per second. To a galaxy racing through that storm, the gas feels like a fierce wind pushing against its face. That pressure can be strong enough to blow away the galaxy's own gas, stripping it from the outside in. The denser the cluster's gas, and the faster the galaxy's motion, the stronger the effect. Astronomers can even calculate when stripping starts with a simple balance. If the external pressure exceeds the galaxy's gravitational grip on its gas, the gas gets torn away. The result is spectacular. Some galaxies develop long trailing plumes of stripped gas and newly ignited stars that shine like comet tails, known as jellyfish galaxies. These luminous tendrils, visible in optical and X-ray light, trace the path of the expelled material as it mixes into the cluster's atmosphere. Over time, the galaxy loses its raw fuel for star formation. Its spiral arms fade, its colors redden, and it evolves into a smooth, quiescent elliptical, an object that remembers its past motion through scars rather than structure. Tidal forces, gravity's uneven pull, work from a different angle. As a galaxy orbits within a cluster or near a larger companion, the outer parts feel a stronger gravitational tug toward the cluster's center than the inner parts do. That difference stretches the galaxy and can shear away stars, dark matter, and globular clusters from its outskirts. The point where the galaxy's own gravity can no longer hold on to material against these external tides defines the tidal radius. Beyond that, its stars drift free, often joining the cluster's faint intragalactic light, a ghostly glow that fills the spaces between galaxies like spilled starlight. Both ram pressure and tidal stripping depend on trajectory and timing. A galaxy plunging straight through a cluster's core experiences intense stripping. One gliding along the outskirts might keep much of its gas. The two processes also often work together. Ram pressure removes gas, while tidal forces remove stars and dark matter. In extreme cases, a small galaxy passing too close to a massive neighbor can be torn apart entirely, leaving behind tidal streams, delicate arcs of stars marking its final orbit. The Milky Way has its own examples. The Sagittarius dwarf galaxy is currently being shredded, its stars forming a long ribbon encircling our sky. Not only do these interactions destroy, but they also recycle. It is possible for stripped gas to mix into the atmosphere of the cluster, where it can cool, compact, and later start new galaxies. Astronomers can figure out how much mass and motion are in groups by adding the light from stars that have been torn off of their hosts. Ram pressure and waves are like the cluster's way of eating galaxies. They break them down and spread their parts out in the bigger world. These boundaries tell us where a galaxy's influence ends. The extent of a galaxy's gas disk marks the limit of its internal ecosystem. The outer halo of stars and dark matter defines how far its gravity can still dominate. When those features are truncated or asymmetrical, astronomers can measure how violently the surrounding environment is interacting with it. High-resolution imaging from the Hubble Space Telescope and X-ray data from Chandra have shown that these processes are common, not rare. They're the engines of galaxy evolution inside dense environments. In cosmological terms, the combination of ram pressure and tidal boundaries gives clusters their living edges. They're places of transformation, where fresh infalling galaxies are stripped, reshaped, and absorbed. Over billions of years, these interactions help turn chaotic collections of galaxies into more uniform, quiescent systems. The interstellar medium, the galaxy's hidden ocean. There is stuff in the space between the stars. The interstellar medium, or ISM, is a huge, unseen material that fills the Milky Way. It is a delicate mix of gas, dust, and magnetic fields that makes up the galaxy's core. This is where all stars, planets, and nebulae came from. It's like a bloodstream for the galaxy, carrying the waste products of stars dying and being born through its twisting arms. The ISM is a moving ocean of shock waves, winds, and radiation that shape the galaxy we live in all the time, even though it looks like a vacuum. Most of the ISM is hydrogen, sprinkled with helium and trace amounts of heavier elements forged in stars. But it's not uniform. Astronomers divide it into phases: cold molecular clouds, warm ionized gas, and hot diffuse plasma, each with its own temperature, density, and personality. In the coldest regions, where temperatures drop below 250 degrees Celsius, hydrogen atoms cling together as molecules, forming dense clouds where gravity can eventually ignite new stars. These molecular clouds are massive, dark, and dusty, often hundreds of light years across. To our eyes, they appear as the black gaps cutting through the Milky Way's bright band, but to radio telescopes, they glow softly in the millimeter wavelengths of carbon monoxide and other molecules. In these clouds, density fluctuations begin to collapse under gravity. As they shrink, the centers grow hot, birthing new stars surrounded by spinning disks of gas and dust. When these stars ignite, their intense ultraviolet light carves glowing H2 regions, bubbles of ionized gas, into the surrounding cloud. These are the stellar nurseries we see as bright pink and red patches in nebulae like Orion. Each new generation of stars, once formed, begins to sculpt its birthplace, heating, stirring, and eventually blowing it apart, spreading the ingredients for the next. But not all of the ISM is calm or cold. Scattered through the galaxy are enormous cavities of hot plasma created by supernova explosions. When a massive star dies, it releases energy equivalent to the output of an entire galaxy in an instant. The blast rips through nearby clouds, compressing some regions and igniting new star formation while clearing out others. Over time, these overlapping shock waves merge, forming superbubbles hundreds of light years wide. The Milky Way's disk resembles a sponge, punctured by these voids, their interiors glowing faintly in soft X-rays. Magnetic fields thread through all of this, shaping how the gas moves. They channel cosmic rays, guide interstellar shocks, and sometimes resist gravitational collapse, delaying star formation. Observations from the Planck satellite and Sophia telescope show that these magnetic filaments are intricately aligned with the shapes of dust clouds, like invisible strings tying the galaxy together. Combined with turbulence from stellar winds and rotation, they create a dynamic, constantly changing medium, a living environment where matter is always in motion. The ISM is also the galaxy's past. It has the ashes of stars that have been dead for a long time, the radiation from stars that are just starting out, and the chemical marks of everything that has ever lived. Everything heavier than helium, like oxygen, carbon, iron, and gold, was made in stars and then returned into this gas. Over billions of years, this enrichment changes the chemistry of the ISM slowly, setting the stage for more complicated worlds. Silicates, ices, and organic molecules are carried by the dust grains that move between stars. These are the building blocks for planets, and finally, life. On a galactic scale, the interstellar medium drives the rhythm of the Milky Way. It cycles matter through what astronomers call the galactic ecology. Stars form in dense clouds, evolve and die in explosions that return enriched material to space. That gas cools, collapses, and forms new stars. This feedback loop keeps the galaxy balanced, neither collapsing under its own weight nor dispersing into nothingness. Even so, the ISM is fragile. Too much supernova activity can blow large chunks of it out of the galactic plane, forming fountains of gas that rain back down later. Too little activity, and the gas grows cold and inert, stifling star formation. The Milky Way's long-term vitality depends on maintaining this balance, a kind of cosmic climate equilibrium governed by energy, gravity, and feedback. Supernova bubbles and galactic winds. Every galaxy breathes, but not with lungs or air. Instead, it breathes through supernova, which are the huge explosions that happen when big stars die. Each explosion gives off enough energy to temporarily shine brighter than a whole galaxy. This sends shockwaves through the interstellar medium, ISM, and changes the structure of the Milky Way from the inside. Large galactic winds are created when these blasts meet and join together. These winds push gas and dust high above the galactic plane. This pattern of death and renewal is what makes galaxies change over time, and in many ways, what limits they can reach. A single supernova releases roughly 10 octillion joules of energy, about what the Sun emits over 10 billion years. That energy doesn't just vanish, it plows into the surrounding ISM, heating gas to millions of degrees, and creating an expanding superbubble of hot plasma. At first, the shock front races outward at thousands of kilometers per second, sweeping up interstellar material like a snowplow. Inside the bubble, the gas becomes so thin and hot that it emits X-rays instead of visible light. Over time, the shell slows down, cools, and merges into the turbulent medium of the galaxy's disk, but its imprint lingers for millions of years. Now multiply that by thousands of stars. In star-forming regions such as the Orion-Eridanus complex or the Carina Nebula, clusters of young, massive stars live fast and die young. Their combined stellar winds and supernovae merge into sprawling networks of superbubbles hundreds of light-years across. Seen in X-rays or radio, the Milky Way's disk is riddled with them, hollow cavities carved out of the ISM, bordered by cooler shells of gas and dust. The Sun itself likely resides on the edge of one such structure called the local bubble, a roughly 1,000 light-year-wide cavity created by ancient supernovae 10 to 20 million years ago. It's this bubble that defines much of our local galactic environment, shaping how the heliosphere interacts with interstellar space. As multiple bubbles grow and overlap, some eventually punch through the galactic disk entirely, venting hot gas into the halo above and below. These galactic chimneys act as exhaust ports, releasing energy and matter into intergalactic space. The process creates fountains of ionized gas that rise thousands of light-years before cooling and raining back down, a phenomenon astronomers call galactic fountains. Observations of galaxies like NGC 3079 and M82 reveal dramatic examples, plumes of glowing hydrogen, tens of thousands of light-years tall, shooting out from their central regions like red smoke from a cosmic volcano. These outflows aren't random, they're self-regulating mechanisms. Without them, galaxies would keep forming stars too rapidly, burning through their gas in a cosmic flash. The winds carry away both energy and metal-rich gas, thinning the interstellar medium and slowing the rate of new star formation. They also distribute heavy elements, oxygen, iron, carbon, far beyond the galaxies themselves, enriching the surrounding intergalactic medium. In this way, supernovae are both the architects and janitors of galactic ecosystems, maintaining balance through violence. At the heart of many galaxies, even more powerful winds arise, not from exploding stars, but from supermassive black holes. When these giants accrete matter, the process releases tremendous amounts of energy that can launch galaxy-scale outflows, sweeping gas out of their host galaxies entirely. In active galaxies, the combination of black hole-driven and supernova-driven winds can be strong enough to shut down star formation altogether, turning a once bright spiral into a dormant elliptical. For the Milky Way, our central black hole, Sagittarius A*, is currently quiet, but evidence in gamma rays and X-rays suggests it once unleashed vast bipolar bubbles stretching 50,000 light-years above and below the disk. These Fermi bubbles are fossilized scars of past outbursts, still glowing faintly as they cool. The outskirts of the Milky Way are shaped by these winds. As gas moves out into the halo, it cools and condenses along lines of magnetic field. This makes strands that move back toward the disk over hundreds of millions of years. This flow fills up the space between the stars and keeps the star-forming cycle going. This creates a feedback loop, a galactic respiration, in which the Milky Way breathes out hot gas rich in metals and breathes in cool, clean material from space between galaxies. If this didn't happen, the galaxy would either die of exhaustion or blow up from its own energy. Understanding galactic winds is key to understanding cosmic boundaries. They determine how much matter a galaxy keeps and how much it shares with its environment. The stronger the winds, the more diffuse a galaxy's outskirts become, blending imperceptibly into the circumgalactic medium, CGM, a vast reservoir of gas that extends hundreds of thousands of light-years beyond the visible stars. The CGM acts as both buffer and bridge between galaxies, a liminal zone where internal and external forces meet. It's here that the Milky Way's outflows mix with the infalling gas of the local group, defining the invisible edge of our home galaxy. The galactic boundary, where the Milky Way meets the halo. Every galaxy has an edge that we can't see. This is where the stars get fewer and fewer, the gas fades, and the gravity starts to weaken. For the Milky Way, that edge is a long way past the bright disk we can see at night. We know spiral arms and glowing nebulae very well. They are just the thick center of the galaxy halo, which is a much bigger and less noticeable structure. This huge spherical area goes out hundreds of thousands of light-years into space and surrounds the Milky Way. It links our galaxy to the bigger world of the local group. In this area, the Milky Way's edges blend into the gap between galaxies, making it hard to tell what is ours and what is the universe's. The halo is not empty. It's a ghostly mix of old stars, dark matter, and hot plasma, held together by the galaxy's gravity. Some of its stars orbit in wild, looping paths, remnants of ancient galaxies that the Milky Way devoured billions of years ago. Streams of these stars still trace the orbits of their shredded homes, forming stellar rivers across the sky like pale threads of memory. The Sagittarius stream, the Orphan stream, and the GD1 stream are all examples, tidal fossils that reveal how our galaxy grew by consuming smaller neighbors. Each stream is both a scar and a signature, showing that galactic boundaries are not static lines, but living records of collisions and mergers. Beyond the stars, the halo contains enormous amounts of hot, diffuse gas, detectable only in X-rays and ultraviolet light. This is the circumgalactic medium, CGM, a kind of atmospheric shell around the galaxy. It holds more mass than all the stars and cold gas in the disk combined, and it plays a crucial role in the Milky Way's evolution. The CGM is both a reservoir and a recycling system. Gas flows out from the disk in supernova-driven winds, cools in the halo, and eventually falls back in, fueling new star formation. Meanwhile, pristine gas from intergalactic space trickles in, mixing with material enriched by stellar explosions. In this way, the Milky Way continually refreshes itself, balancing outflow and inflow like a cosmic heartbeat. It's clumpy, organized, and magnetized. This halo isn't uniform. It has strands and bubbles, some of which stretch tens of thousands of light-years, as seen by the Hubble Space Telescope and the Chandra X-ray Observatory. The most interesting of these are the Fermi bubbles, which are two huge bands of hot gas and high-energy particles that go above and below the center of the galaxy. They probably get their power from an old burst of activity from Sagittarius A star, the Milky Way's supermassive black hole. They show where the central region's impact ends, showing that even galaxies have weather systems. The outer edge of the halo is defined less by a sharp border and more by a gradual thinning of matter. At distances of about 250,000 to 300,000 light-years, the density of gas and dark matter drops enough that the Milky Way's gravitational pull begins to weaken, relative to the broader tug of the local group. Beyond that lies a transitional zone where the halos of the Milky Way and the Andromeda Galaxy, M31, start to overlap. Simulations suggest that these two halos are already touching, long before the galaxies themselves will collide. In a few billion years, they will merge into a single, giant, elliptical galaxy, an event that will erase the Milky Way's individuality but expand its boundaries into something new. At the edge of this halo, gravity and cosmic expansion meet in a delicate balance. Within it, gas and stars orbit the galactic center. Beyond it, they drift away with the universe's general flow. This balance point, our galaxy's turnaround radius, marks the last region that will remain gravitationally bound to the Milky Way as the universe continues to expand. Everything beyond will eventually cross the cosmic event horizon and disappear from view, while everything within will remain forever tied together by gravity. Studying the galactic boundary gives astronomers a way to understand how galaxies grow and how they interact with their environment. Instruments like FAST, ALMA, and upcoming missions such as LUVOIR and Athena aim to map the Milky Way's halo in unprecedented detail. They will measure how much gas it holds, how it's magnetized, and how it moves. Already, we know that this halo acts as the Milky Way's lungs, exhaling and inhaling gas across cosmic time. It also functions as a shield, deflecting and filtering radiation and cosmic rays that travel between galaxies. But for all its immensity, the halo is still just one layer in a grander structure. Beyond it lies the local group's shared envelope of dark matter and gas, and beyond that, the filaments of the cosmic web that connect us to neighboring clusters. There's no definitive point where the Milky Way stops and intergalactic space begins, only a smooth fade from something dense and personal to something vast and collective. So the edge of the galaxy is not so much a wall as it is a barrier, a place where things change and pass each other. The Milky Way's impact is weakest there, and the last bound gas clouds drift into the quiet space between galaxies. This is also where the story of our galaxy meets the story of the universe as a whole. If you stood at this edge, if that were possible, you would see our galaxy's stars fade into a faint haze, the gas get colder and less common, and the Milky Way's big curve fade behind you until it looks like a faraway bright line across the darkness. The Heliosphere, heliopause, and the interstellar frontier. The world has limits even on the smallest scales, like our own backyard. Every star, including the Sun, makes its own little bubble in space. This is where its energy, wind, and magnetic field push back against the thin clouds of gas and dust that float between the stars. The heliosphere is this huge bubble, and the heliopause, which is the tip of it, shows where the Sun's impact ends. Beyond it starts the interstellar medium, which is the area between stars that is not part of our solar system, but of the galaxy as a whole. The heliosphere exists because the Sun constantly emits a flow of charged particles called the solar wind. Moving at hundreds of kilometers per second, this stream inflates a cavity in the surrounding interstellar gas, a bit like a boat's wake pushing aside water. Near Earth, that wind is still strong. It carries the magnetic field that shapes auroras and protects us from cosmic rays. But the farther it travels, the weaker it becomes. Eventually, it slows to subsonic speeds at a region known as the termination shock, about 90 times farther from the Sun than Earth's orbit. Beyond that, the wind continues to drift outward until it meets the opposing pressure of the interstellar medium. Where the two forces balance, the flow stops expanding. That boundary is the heliopause, the solar system's outer skin. For decades, the heliopause was purely theoretical. Then, in 2012, Voyager 1, launched back in 1977, crossed it. The spacecraft recorded a sudden jump in the density of charged particles coming from interstellar space and a drop in solar particles, confirming it had left the heliosphere. Voyager 2 followed in 2018, crossing at a slightly different distance. Their journeys gave humanity its first direct measurements of the space between stars. Beyond the heliopause, the magnetic field tilts differently. Cosmic rays grow more intense, and the solar wind's influence fades almost entirely. Voyager's instruments, still faintly alive, are now drifting through the interstellar frontier, an achievement that makes our solar system's bubble feel both small and extraordinary. The shape of the heliosphere isn't a perfect sphere. Because the Sun is moving through the local interstellar cloud, a thin wisp of gas and dust, it's thought to be blunt in front and stretched behind, forming a comet-like tail that trails for hundreds of billions of kilometers. The overall size of the heliosphere changes with solar activity. During solar maximum, when the Sun's magnetic field is turbulent and powerful, the boundary swells outward. During solar minimum, it contracts slightly. This breathing motion means the edge of the solar system isn't fixed, but living and rhythmic. The heliopause matters for life as much as for exploration. It acts as a shield, deflecting many high-energy cosmic rays that could otherwise bombard the inner solar system and damage planetary atmospheres. Without it, Earth's surface radiation levels would be higher, and life might have evolved differently. That protective bubble also stabilizes conditions for space weather, allowing planets to maintain magnetic fields and atmospheres for billions of years. Beyond the heliopause lies the interstellar medium, ISM, a mixture of gas, dust, and magnetic fields that pervades our Milky Way. The ISM is incredibly tenuous, with just a few atoms per cubic centimeter, but it's the raw material from which new stars and planets eventually form. As the Sun moves through it at about 230 kilometers per second, the heliosphere interacts with this gas, creating a thin bow wave ahead of us and possibly a trailing wake of charged particles behind. In the distant future, tens of thousands of years from now, the solar system will drift into new regions of the galaxy, where conditions may compress or reshape the heliosphere entirely. In our case, the heliopause is a microcosmic horizon, which means it is a smaller version of the big cosmological borders that shape the universe. On the inside, the Sun's gravity, radiation, and magnetic field control things. On the outside, the climate of the galaxy takes over. We've seen this story play out over and over again at all levels of the universe. Every structure, from stars and groups to the universe itself, has a zone of control that gives way to something bigger in the end. The Oort Cloud and the solar system's true edge. The most distant and strange part of our solar system is the Oort Cloud. It is far away, past Pluto and the scattered Kuiper belt. It's a huge sphere of icy bodies that forms a faint halo around the Sun and goes out to the nearest stars. The heliopause is where the Sun's magnetic field ends, and the Oort Cloud is where its gravity field ends. This is where the Sun's pull is finally replaced by the Milky Way's tides. The Oort Cloud was first proposed in 1950 by Dutch astronomer Jan Oort to explain the strange orbits of long-period comets, those that appear suddenly in the inner solar system with trajectories that can take tens of thousands or even millions of years to complete. Such comets couldn't have originated in the flat, disc-shaped Kuiper belt. Their orbits come from all directions, forming a roughly spherical distribution. The only explanation was that a distant reservoir of icy bodies surrounds the Sun, occasionally sending a few inward after they're nudged by passing stars or galactic tides. The Oort Cloud likely begins around 2,000 astronomical units, AU, from the Sun, about 300 billion kilometers, and may extend as far as 100,000 AU, nearly 2 light-years. It contains an estimated trillions of icy objects, from small comet nuclei to frozen mini-worlds 100 kilometers across. Most of them have been untouched since the birth of the solar system, preserving the original ingredients of the Sun's protoplanetary disk. If we could ever study one up close, we'd be holding a time capsule from 4.5 billion years ago. But how did this distant cloud form? The most widely accepted picture is that, in the early solar system, countless icy planetesimals formed near Jupiter and Saturn. Many were flung outward by the giant planet's gravity, their orbits stretched into vast ellipses. A fraction of them escaped entirely, but others were slowed by interactions with the galactic environment, passing stars, molecular clouds, and the combined gravitational field of the Milky Way. Over time, these perturbations scattered their orbits randomly, creating a huge, nearly spherical cloud of debris. What began as a flat disk of ice and rock became a bubble surrounding the Sun. Within the Oort Cloud, astronomers distinguish between two regions: the inner Oort Cloud, sometimes called the Hills Cloud, and the outer Oort Cloud. The inner region, lying a few thousand to tens of thousands of AU away, may be a denser zone where most of the material resides and where orbits are only slightly elongated. The outer cloud, stretching to the solar system's ultimate edge, contains objects only loosely bound to the Sun. A gentle tug from a passing star or a tide from the galactic center can easily send them drifting away or falling inward, beginning a journey of millions of years that ends as a spectacular comet blazing through our skies. Every long-period comet we see, like Comet Hale-Bopp or Comet Ison, is a messenger from that far frontier. As these comets approach the Sun, heat vaporizes their frozen ices into glowing tails of gas and dust, revealing materials unchanged since the dawn of the solar system. Once their orbits are altered by the planets, many are lost forever, ejected into interstellar space or consumed by the Sun. But for every comet that falls inward, countless others remain, drifting unseen in the dark, preserving the memory of our system's birth. The outermost edge of the Oort Cloud is where the Sun's gravity and the galactic tide balance each other. Beyond that distance, the Milky Way's pull dominates, and objects are no longer gravitationally bound to our star. This boundary, sometimes called the Heliosphere limit of the Sun, marks the solar system's true gravitational edge. It's the final border between what belongs to the Sun and what belongs to the galaxy. The distance ladder and the limits of cosmic measurement. How well we can measure space is key to knowing where the world ends, and that has always been one of the hardest things about astronomy. Astronomers made a cosmic distance ladder because a tape measure can't be stretched across light years. This ladder is made up of ways that work together and go from the solar system to the edge of what we can see in the universe. Each rung makes the next one work right, but like any ladder, it has its boundaries. At some point, the steps become less stable, and it becomes harder to tell where the next rung might be. The first rung is parallax, the apparent shift of nearby stars against the background as Earth orbits the Sun. Its geometry, pure and simple. Ancient astronomers couldn't detect parallax at all. The shifts were too tiny. Today, space telescopes like Gaia can measure angles smaller than a millionth of a degree, mapping distances to stars thousands of light years away with exquisite precision. Parallax is the foundation, a directly measured baseline that anchors everything else. Astronomers rely on standard candles, objects whose intrinsic brightness is known, so their apparent dimness reveals their distance. The most famous are Cepheid variable stars, whose brightness pulses in a way that correlates precisely with their true luminosity. Henrietta Swan Leavitt discovered that relationship in 1912, and it became the key to unlocking galaxies far beyond our own. When Edwin Hubble measured Cepheids in the Andromeda Nebula in the 1920s, he proved it was an entirely separate galaxy, and the universe suddenly expanded in scale by orders of magnitude. The next rung uses even brighter markers, type Ia supernovae. These stellar explosions always reach about the same peak brightness, allowing astronomers to spot them across billions of light years. By comparing their observed light curves to the standard pattern, scientists can determine distances to faraway galaxies. And by combining those distances with redshift, they measure the expansion rate of the universe, known as the Hubble constant. It's this very technique that revealed the acceleration of cosmic expansion and hinted at the existence of dark energy in the late 1990s. But no method is perfect. Each step depends on the calibration of the one before it, and even tiny mismatches ripple upward. Disagreements between distance indicators, especially between local measurements, from Cepheids and supernovae, and early universe values inferred from the CMB have led to what's now called the Hubble tension. It's a reminder that our cosmic ladder is built on fragile connections. The farther we climb, the more errors can accumulate. Whether this tension is a sign of new physics or just unrecognized systematic bias remains one of cosmology's biggest open questions. We use other methods to fill in the holes. Changes in surface brightness use the graininess of galaxy light to figure out how far away something is. The light of a galaxy is linked to its spin speed or velocity dispersion by the Tully-Fisher and Faber-Jackson relationships. Time delays caused by gravitational lensing, differences in when light arrives because of heavy things warping space, now serve as their own distance marks. While each one makes the ladder stronger, they all reach their own noise limit over time as things get smaller and light from the sun goes further into the infrared. In the farthest reaches, where even supernovae fade beyond detection, we rely on redshift surveys, the Doppler-like stretching of light caused by expansion. Redshift doesn't measure distance directly, but when combined with a cosmological model, it tells us how far back in time we're looking. The highest confirmed galaxy redshifts today correspond to about 13.5 billion years of look-back time. The faintest ones, seen by the James Webb Space Telescope, are near the boundary where the first galaxies formed, only a few 100 million years after the Big Bang. The distance ladder shows that edge is partly a function of technology. As instruments improve, from parallax measurements by Gaia to deep field imaging by JWST, the horizon of the measurable universe expands. Yet, beyond a certain point, even light becomes too faint, too stretched, or too absorbed to detect. At that scale, our cosmic ladder doesn't break. It simply fades into darkness. Standard sirens and new cosmic horizons. Light has been our way of measuring the world for more than 100 years. But light can be absorbed, spread, and changed in color until it is so dim that it can't be seen. Now there is a new messenger in the story. It doesn't dim or spread, and its signal has information about how far away it is built right into it. They are gravity waves, and when they are used to show how far away something is, they are called standard alarms. They promise to help us reach further into space, past the range of photons. The term standard siren was coined as a gravitational wave analog to standard candle. Where a supernova's brightness reveals how far away it is, a gravitational wave's amplitude, its strength when it arrives, does the same. Because the laws of general relativity tell us exactly how gravitational waves weaken with distance, the observed strain directly encodes how far the source must be. Combine that distance with a redshift from any accompanying light, and you have an independent way to measure cosmic expansion. No calibration steps required. The first glimpse of this new cosmic ruler came in 2015, when the LIGO detectors caught the merger of two black holes, the first confirmed gravitational wave event in history. Then, in 2017, something even more extraordinary happened. LIGO and Virgo detected the collision of two neutron stars, while telescopes around the world caught the flash of light from the same event. The merger, dubbed GW 170817, provided both a gravitational signal and a traditional electromagnetic counterpart. For the first time, scientists could directly compare the gravitationally measured distance with the redshift of its host galaxy, effectively taking a new kind of cosmic measurement without relying on the old distance ladder. That single event already yielded a new, independent estimate of the Hubble constant, the rate of the universe's expansion. It wasn't as precise as traditional methods, but it didn't depend on any of their assumptions. As more detections accumulate, gravitational waves could help resolve or deepen the Hubble tension between early and late universe measurements. In the coming decade, advanced detectors like LIGO India, CAGRA, and the Einstein telescope, along with space-based missions such as LISA, Laser Interferometer Space Antenna, will multiply our catalogue of standard sirens many times over. Beyond measuring distances, gravitational waves carry clues about the cosmic history of structure and star formation. Binary black hole mergers trace the life cycles of massive stars across the universe. Their rate tells us how galaxies evolved. Mergers of neutron stars reveal where heavy elements like gold and platinum are born. The waves themselves travel unimpeded through dust and gas, letting us peer into regions light could never reach, like the hearts of merging galaxies or the dense centers of star clusters. In theory, gravitational waves could even probe the very early universe, long before it became transparent to light. Processes such as inflation, phase transitions, or the formation of cosmic strings might have generated a primordial gravitational wave background, a faint hum permeating all of space. Unlike photons, which were trapped until 380,000 years after the Big Bang, these ancient waves would have streamed freely from the universe's first moments, carrying information about physics at energies far beyond anything we can test on Earth. The larger toolkit of astronomy is strengthened by standard sirens. When electromagnetic data are added, they can make new maps of how fast the universe is expanding. Check to see if gravitational waves move at the same speed as light. They do, amazingly accurately, and see if gravity acts differently at the largest scales. It's most likely that we'll find any deviations from general relativity in these cracks in space. The Planck scale, where physics breaks down. The limits we've looked into, like cosmic gaps, event limits, and gravity edges, still work within the rules of what we know about physics. But there is one last area where these rules stop working. The Planck scale, which is the universe's smallest meaningful size. This is where gravity, quantum physics, and reality itself stop acting in their own ways. After this point, our equations don't make sense, and the word distance might not even exist anymore. The Planck scale is built by combining three of nature's fundamental constants: the speed of light, c, Newton's gravitational constant, g, and Planck's constant, h, which defines the quantum realm. When these three are brought together, they form natural units that represent the boundaries of known physics. The Planck length, about 1.6 times 10 to the power of minus 35 meters, is thought to be the smallest possible unit of distance. The Planck time, around 5.4 times 10 to the power of minus 44 seconds, is the briefest possible moment. And the Planck energy, roughly 10 to the 19th giga-electron volts, marks an energy so extreme that our current theories of quantum mechanics and gravity can no longer accurately describe what happens. At these scales, quantum fluctuations in energy and geometry become so intense that space-time would appear turbulent, a quantum foam of constantly forming and annihilating microscopic black holes. Smooth geometry breaks down into a froth of probability. The concept of a point in space or a continuous timeline stops being meaningful. Instead, reality may be quantized, made of discrete chunks of space-time. It's the ultimate limit on how small or how early we can explore the universe. We can also see back in time up to a certain point on this scale. The cosmic microwave background, which is the oldest light we can see, tells us that the universe is about 380,000 years old. Neutrinos take us back in time 1 second. You might be able to feel gravitational waves from a very short time after the Big Bang. We don't yet have a theory that combines quantum physics and gravity, which is what we'd need to look further back than the Planck time, when the universe as a whole was smaller than a proton. That's why cosmologists say the Planck epoch a lot of the time. Our science can't go any further than that. Several theoretical frameworks aim to describe this regime. String theory proposes that all particles are actually vibrating one-dimensional strings whose length is on the order of the Planck scale. Loop quantum gravity imagines space-time itself as a network of finite loops, like a fabric woven from quantum threads. Other ideas invoke quantum geometry, or higher dimensional spaces that compactify at microscopic scales. None has been proven, but all share one implication. Space and time may be emergent properties, not fundamental ingredients of reality. The Planck scale isn't just a lower limit, it's a boundary of knowledge. We can't test it directly because no particle accelerator or cosmic event within our reach can produce such energies. Even the most powerful phenomena we observe, like gamma-ray bursts or supernovae, fall many orders of magnitude short. To recreate Planck-level conditions would require compressing more energy than the entire mass of Mount Everest into a volume smaller than an atom. That's beyond imagination and beyond experiment. Yet, indirect hints may come from the cosmos itself. Tiny distortions in the polarization of the CMB, minute deviations in the spectrum of primordial gravitational waves, or the behavior of black holes as they evaporate, could all encode traces of Planck-scale physics. The quantum structure of space-time might subtly influence how the universe expands, how information is preserved in black holes, or even how nothing gives rise to something. These faint clues are the only paths we have toward understanding what happened at the ultimate beginning. The Baryon budget and the case of the missing matter. Astronomers thought they had a good understanding of what the universe was made of for many years. Dark energy makes up about 68% of the universe's total mass. Dark matter makes up about 27%. And regular matter, or baryons, makes up the last but very important 5%. Protons, neutrons, and electrons are what make up these baryons. They are what make up stars, planets, and people. But scientists couldn't find half of those baryons when they tried to count them all. The search for them turned into one of the most confusing quests in astronomy, and it changed the way we think about where the edges of matter really are in the universe. The mystery began with predictions from Big Bang nucleosynthesis, the process that forged the first light elements minutes after the Big Bang. Those calculations, confirmed by the cosmic microwave background, tell us exactly how many baryons should exist per cubic meter of space. But when astronomers tallied up all the stars, gas, and dust in galaxies, they found only about half of that expected total. Even after including the hot gas inside clusters of galaxies, there was still a huge deficit. Where had the rest of the matter gone? The answer, it turns out, was hiding in plain sight, spread thin across the intergalactic medium. Using ultraviolet and X-ray telescopes, scientists discovered that most of the missing baryons reside in the warm-hot intergalactic medium, WIM, an enormous web of diffuse gas at temperatures between 100,000 and 10 million degrees. This gas is too hot to emit visible light, too cool to glow in X-rays, and too diffuse to detect easily. But its presence can be traced through faint absorption lines, imprinted on the spectra of distant quasars, particularly those of oxygen and hydrogen ions. Each line corresponds to a specific temperature and density, revealing invisible threads of matter connecting galaxies across cosmic space. In 2018, an international team confirmed these elusive structures using pairs of distant quasars. When light from two quasars passed through the same region of space, both spectra showed matching absorption lines, indicating a filament of hot gas stretching between galaxies. This was the missing baryonic glue of the cosmic web, material that had been predicted by simulations for years, but only now directly observed. By adding up the contributions from all such filaments, the missing half of the baryons finally reappeared, closing one of cosmology's most persistent gaps. Finding the WIM did more than solve a puzzle. It showed that the universe's boundaries of matter are porous. Most of the baryons aren't locked in stars or planets, but drift between galaxies, heated by shocks from structure formation and feedback from black holes and supernova. These processes constantly recycle matter, sending it out of galaxies and back into the intergalactic medium. The universe, then, isn't divided neatly into galaxies and emptiness. It's a continuous ecosystem of inflow and outflow, where matter and energy flow across invisible borders. This discovery also changes how we interpret the edges of galaxies and clusters. The visible parts, spiral arms, halos, and bright cores, are only the densest peaks of a much larger reservoir. Gas stripped by winds, jets, and tidal forces can extend millions of light-years into space, gradually merging with the WIM. Even the local group's environment is threaded by such faint bridges, linking the Milky Way and Andromeda in a shared envelope of plasma. When we say a galaxy ends, we're really describing where its matter becomes too diffuse for us to see. The WIM also plays a vital role in cosmic evolution, It regulates the growth of galaxies by controlling how much gas they can accrete, acts as a highway for heavy elements ejected by supernovae, and provides the raw material for future star formation. Understanding its density, temperature, and motion helps refine our models of structure formation and the universe's energy balance. The missing baryons weren't lost, they were just spread too thin for earlier instruments to find. Dark matter's halo, the hidden skeleton of the universe. Light matter paints the picture of the universe, and dark matter builds the stage. It makes up almost 85% of all matter, but it doesn't give off or take in light. Even though we can't see it, we can see how its gravity shapes galaxies, groups, and the cosmic web itself. There is an unseen halo of dark matter around every star, spiral arm, and group of galaxies. This halo is much bigger and heavier than all the bright matter put together. Even though they can't be seen, these halos show where the real edges of galaxies are. The idea of dark matter arose in the 1930s, when Swiss astronomer Fritz Zwicky noticed that galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. Decades later, Vera Rubin measured the rotation curves of spiral galaxies and found they didn't slow down with distance from the center as expected. Instead, stars at the edges orbited just as quickly as those near the core, implying an unseen mass extending far beyond the visible disk. Something invisible, but gravitationally dominant, was holding galaxies together. Simulations later revealed how dark matter behaves on cosmic scales. It forms a network of filaments and halos that attract ordinary matter, acting as a gravitational scaffold on which galaxies form. As gas cools and condenses inside these halos, stars ignite, creating the bright structures we see. The halos themselves can be 10 to 100 times more massive than their visible counterparts. For a galaxy like the Milky Way, the dark halo extends roughly 1 million light-years, enveloping not just the stars and gas, but also the Magellanic Clouds and other satellite galaxies. When galaxies merge, their halos fuse and grow, feeding the ever-expanding cosmic skeleton. The structure of these halos follows a remarkably consistent pattern, known as the Navarro-Frank-White profile, dense in the center, tapering gradually outward. But unlike stars or gas, dark matter is collisionless. It doesn't clump, radiate, or interact except through gravity. That's why halos are smooth, diffuse, and stable over billions of years. They provide the gravitational wells that trap baryons, guiding where galaxies can form and how large they can grow. Evidence for dark matter halos comes from many directions. Gravitational lensing, the bending of light around massive objects, reveals the mass of clusters and galaxies, regardless of whether it's luminous. In clusters like Bullet Cluster, collisions between galaxies show that most of the mass, and therefore most of the gravity, lies in regions displaced from the visible gas, confirming dark matter's presence as a separate, invisible component. The large-scale distribution of galaxies also matches what we'd expect from a universe dominated by dark matter. Without it, cosmic structures couldn't have formed so quickly after the Big Bang. Despite this overwhelming evidence for its gravitational pull, we still don't know what dark matter is. It might be made of exotic particles such as WIMPs, weakly interacting massive particles, axions, or even sterile neutrinos, none of which have been detected yet. Experiments buried deep underground, submerged in ice, or orbiting in space continue to search for faint hints of collisions between dark matter particles and ordinary atoms. So far, the detectors remain silent, but the quest continues with ever-increasing sensitivity. Whatever its nature, dark matter defines the true extent of cosmic structures. A galaxy's visible stars mark only its bright heart. The dark halo is the body that holds it together. The edges of these halos blur into one another, connecting galaxies across filaments into clusters and superclusters. In this way, dark matter doesn't just bind galaxies, it binds the universe into a single interconnected whole. Without it, cosmic expansion would have scattered matter too evenly for stars or planets ever to form. Even on the largest scales, dark matter leaves a distinct fingerprint. Its distribution determines how galaxies cluster, how light bends as it passes through space, and how cosmic expansion accelerates or slows. By mapping these effects, astronomers can reconstruct the hidden skeleton of the universe with remarkable precision. Future missions like Euclid and the Nancy Grace Roman Space Telescope aim to chart dark matter's distribution using weak lensing, turning invisible mass into measurable structure. Even though dark matter's impact goes far beyond the visible world, it still has limits. Dark energy's pull is stronger than even dark matter's gravity at very large distances, stretching space-time faster than objects can grow. Once you go past that point, halos stop combining, strands get thinner, and the cosmic web starts to stay put. The freeze-out of structure, when gravity loses the battle. There is a time for every force in the world. In the first few billion years, gravity pulled matter into galaxies, clusters, and filaments. But dark energy is winning in this cosmic age. Space is getting stretched out faster than gravity can pull it back together because the world is expanding faster. This change means that the structure of the universe has frozen out. At this point, no new big structures will ever form. The universe will keep growing past this point, but its big structure will stop changing. In the early universe, matter was packed tightly enough for gravity to work efficiently. Tiny density ripples, amplified over time, collapsed into the cosmic web we see today. As the universe expanded, the density of matter decreased, while the density of dark energy, apparently constant, stayed the same. A few billion years ago, those two energy components became equal. From then on, dark energy began to dominate, accelerating the expansion and driving galaxies apart faster and faster. In regions where gravity still holds sway, inside galaxies and clusters, structures remain bound. But on larger scales, the expansion now acts like a cosmic wind blowing everything apart. Filaments between clusters are stretching thinner. The flow of matter into halos has slowed to a trickle. Simulations show that within the next few tens of billions of years, growth will grind to a halt entirely. The large-scale map of the universe will be frozen, not because time stops, but because gravity can no longer bridge the widening gaps. This freeze-out doesn't destroy what already exists, it isolates it. Each gravitationally bound region becomes a cosmic island, forever cut off from others by the accelerating expansion. In our corner of space, the local group, the Milky Way, Andromeda, and their satellites will merge into a single elliptical galaxy, sometimes called Milkomeda. Everything beyond our supercluster's turnaround radius will drift away, eventually crossing our event horizon and disappearing from sight. In a few 100 billion years, even the nearest galaxies will vanish from our observable universe, leaving future observers with a lonely, static sky. From a scientific perspective, this freeze-out defines a new kind of boundary, not a wall in space, but a limit in time beyond which structure formation stops. Astronomers already see evidence of this slowdown. Observations of galaxy clusters show that their growth rate is declining. The abundance of massive clusters at different redshifts acts as a clock for cosmic acceleration. The fewer new clusters we see forming, the stronger the pull of dark energy must be. The data fits perfectly with predictions of a universe heading towards structural stasis. This change also prepares the universe for the end we talked about earlier, called the heat death. When structure formation stops, galaxies stop getting new fuel, black holes stop getting new food from mergers, and the rate of star formation drops sharply. The world goes from being created to slowly breaking down and losing its light. But the freeze-out is an important event in and of itself. It's when the universe stops expanding and starts just existing. The exact timing of this freeze-out depends on the properties of dark energy. If dark energy's density changes over time, the schedule could shift. A slightly stronger acceleration would isolate structures sooner. A weakening one could allow some growth to continue. Measuring the equation of state of dark energy, how its pressure relates to its energy density, is one of the biggest goals of modern cosmology. Missions like Euclid and Roman aim to track this transition precisely by observing galaxies and supernovae across cosmic history, peculiar velocities, and the blurred edge of expansion. When we think of the universe growing, we often picture galaxies being spread out evenly on a space-time cloth that is stretching. But things are harder in real life. In addition, each galaxy has its own unique speed, which is caused by gravity pulls from other galaxies nearby. These small changes make the field of cosmic expansion look a little wonky. They add texture and noise to the Hubble flow, which is normally smooth. Astronomers can figure out how the universe is expanding by studying these strange moves. This shows that even the edge of expansion of the universe isn't a smooth, solid limit. Let's start with the Hubble-Lemaitre law, which says that galaxies move away from us at speeds proportional to their distance. In simple form, it's written as v equals h naught times d, where v is the recession velocity, h naught is the Hubble constant, and d is the distance. On very large cosmic scales, this relationship holds perfectly, but on smaller scales, within clusters and superclusters, local gravity adds complications. Galaxies tug on one another, creating extra motion beyond the general expansion. For example, our Milky Way is moving at about 600 kilometers per second relative to the cosmic microwave background. This motion is partly caused by the pull of the Great Attractor, a huge concentration of galaxies about 200 million light-years away. These local effects produce small deviations from the smooth Hubble flow, like eddies in an otherwise steady cosmic current. Inside clusters, peculiar velocities dominate completely. Galaxies swirl around at thousands of kilometers per second, orbiting the cluster's center of mass rather than following the universal expansion. That's why clusters themselves don't expand. Their gravity is strong enough to resist the Hubble flow. Between clusters, however, space expands freely, stretching the distances between these bound systems. On intermediate scales, both effects mix, making it tricky to define exactly where expansion begins to win over local motion. Astronomers can map these flows by comparing galaxies' redshifts, which show total motion, with independent distance measurements from standard candles like Cepheids or supernovae. The difference between the two reveals the peculiar velocity, the part not caused by expansion. By collecting these data for thousands of galaxies, cosmologists can create a velocity field map of our local universe. The result is a dynamic picture. Clusters drawing galaxies inward, voids pushing them outward, and the overall flow superimposed on the smooth backdrop of expansion. Peculiar velocities are important because they distort all of our measurements at a big scale. Galaxies that fall into a cluster look a little closer than they really are when we look at redshift scans. This effect is called the finger of God in redshift space. When looking at things on a bigger scale, coherent in falling toward massive objects makes the visible distribution of galaxies spread, which makes minor anisotropies. For accurate astronomy, fixing these errors is very important. Not only are they annoying, but they also tell us something about how mass is spread and how gravity works in the cosmic web. Over time, peculiar motions fade. As the universe expands and dark energy dominates, the overall density of matter decreases, weakening the gravitational interactions that drive these motions. Simulations predict that peculiar velocities will gradually slow, and eventually, galaxies outside gravitationally bound regions will settle into an almost perfectly uniform Hubble flow. The local ripples in expansion will smooth out as cosmic acceleration erases the memory of early gravitational clustering. These motions are essential reminders that the universe is not a static painting. It's alive with movement. Every galaxy we observe is both part of the universal expansion and a participant in its own gravitational dance. These competing motions define what we mean by edge. There isn't a fixed line where expansion starts, only a gradual transition from local gravity's dominance to the global flow of space. Our own Milky Way sits in one such boundary region. Within a few million light-years, gravity keeps the local group intact, but beyond roughly 5 million light-years, galaxies start participating fully in the Hubble expansion. That boundary, constantly shifting and slightly blurred by peculiar motions, is our local horizon, the smallest scale version of the cosmic balance between attraction and expansion. The final messengers, neutrinos, cosmic rays, and the quieting universe. Starlight, galaxies, and even the cosmic microwave background will become less loud as the universe gets older and less full. But even after the last star dies, neutrinos, cosmic rays, and the faint hum of gravitational waves will still be able to get their message across. These particles and ripples are the last ones in the world that can still send and receive messages over long distances, even though almost everything else has stopped talking. Right now, neutrinos stream everywhere. They are ghostly, nearly massless particles that interact so weakly with matter that trillions pass through your body every second without leaving a trace. Born in nuclear reactions within stars, in exploding supernova, and even in the early moments of the Big Bang, they form an invisible cosmic sea. The cosmic neutrino background, frozen just 1 second after the Big Bang, still fills all of space, older and colder than even the microwave background. Detecting it directly remains one of the great experimental challenges, but its gravitational fingerprints are already woven into the fabric of cosmic structure. Neutrinos will still be around long after galaxies have died out, and light is hard to come by. As the universe expands, they lose almost no energy. In fact, they redshift so slowly that they will last longer than the CMB and any electromagnetic wave. Even in the utmost silence of cosmic heat death, they will still be there, floating on and witnessing everything that came before. Cosmic rays tell another story of endurance. For now, they are the universe's high-energy bullets, atomic nuclei accelerated by violent astrophysical engines like supernova remnants, pulsars, and active galactic nuclei. They zip across the universe near light speed, sometimes striking Earth and producing showers of secondary particles in the atmosphere. But their reach has limits. Collisions with the cosmic microwave background impose the GZK cutoff, capping how far the most energetic cosmic rays can travel. As the universe expands and cools, that fog of background photons will thin and redshift, allowing lower energy cosmic rays to travel even farther. Yet cosmic acceleration ensures that future cosmic rays will have fewer targets and weaker engines to launch them. The last bursts of star formation will fade. The magnetic fields that help accelerate these particles will decay. Over eons, the skies will grow still as even cosmic rays run out of sources. Then there are the faint tremors of gravitational waves, ripples in space-time from merging black holes and other cataclysmic events. These waves cannot be blocked or absorbed, making them the most durable signals of all. As stars vanish and matter evaporates into radiation, only black holes will remain to send their last whispers through the void as they merge or evaporate. Even in the universe's quietest age, the gravitational wave background will persist as a lingering memory of every collision that ever was. These final messengers form a kind of cosmic afterglow, far fainter than light, but far more enduring. They represent the last ways energy and information can move through space once the luminous universe has dimmed beyond visibility. For future observers, if any exist, they would be the only clues that there was once a cosmos filled with light, galaxies, and life. The information horizon, when the universe forgets itself. What we can see is set by each limit we've met so far: the cosmic, the event, and the gravity. The knowledge horizon is the last type of limit that tells us what the world can remember. In the past of the universe, this is the point at which entropy is highest, and all memories of structure, light, and contact are lost forever. The world doesn't just get quiet beyond this point, it forgets. In physics, information isn't a poetic idea, it's the measure of order encoded in particles, fields, and quantum states. The second law of thermodynamics says entropy, the measure of disorder, always increases. As stars burn, as black holes swallow matter, and as radiation spreads out, the universe steadily moves from complexity to uniformity. Every irreversible process, every supernova, every merger, every decay, erases fine details about its starting conditions. Over trillions of years, the universe's story gets rewritten in coarser and coarser print. For a while, black holes seemed to be the perfect information vaults, objects so compact that nothing, not even light, could escape. But when Stephen Hawking discovered that black holes slowly radiate energy, another paradox emerged. If they evaporate completely, what happens to the information about what fell in? Quantum theory insists that information can't be destroyed, yet Hawking's calculations implied that it vanishes with the black hole. Decades of debate followed, spawning what physicists call the black hole information paradox. Most modern interpretations suggest that the information isn't lost, but is somehow encoded in the outgoing radiation or on the event horizon itself in a holographic form. That idea, the holographic principle, extends far beyond black holes. It proposes that all the information contained within a region of space can be represented by bits on its boundary, like a cosmic data screen. In other words, the universe might be a hologram, with every event on the inside written in fine detail on the edge. The cosmic event horizon of our accelerating universe might function in a similar way. As space expands, more of the universe slips beyond our reach, but its information may be projected on this boundary, preserving it in principle, even if we can never retrieve it. But in real life, even that number gets worse over time. When the last black holes die off, which will happen in trillions and trillions of years, their last bursts of Hawking radiation will spread out over a universe that has grown incredibly big. Each photon will carry a quantum hint of the information that was locked inside, but it will be spread out so much that it can't be recovered. It will have reached what scientists call maximum entropy, which means that all of the universe's forces will be balanced. There are no slopes, differences, or chances for things to change. It will still be there, but it will look like a completely flat, dull sea of energy. In this final state, all distinctions vanish. The difference between one region of space and another, between one particle and another, between past and future, all dissolve into uniformity. Time, as we experience it, is driven by entropy's arrow, by the progression from order to disorder. Once entropy can't increase anymore, that arrow loses direction. The universe will still have time, but nothing meaningful will happen in it. So, the universe doesn't end with a wall or a flame. It fades into silence, a vast ocean of expansion, where even memory itself dissolves. Every boundary we can imagine, from the heliopause to the cosmic horizon, reminds us how small our window of knowing truly is. But that's what makes it worth exploring. If you want to keep traveling further into these cosmic frontiers, make sure to like, subscribe, and watch the next video on your screen, because the story of the universe is far from over.